All right. So this is a Tag 5 Oregon. This is our 5th and final tag meeting, unless there is a needed 6th tag meeting, which we'll discuss later. Today we'll be discussing distribution system planning and some finalization of plan components. So I'm going to go through the agenda. We'll go through introductions. First off, I'm Brian Robertson, Supervisor of Resource Planning with Cascade. I'll go through a safety moment, and we like to touch on the stakeholder engagement document at every tag meeting. And then Kathleen will give a presentation on our distribution system planning. Ashton will discuss backcast overview and summary of alternative resources. I'll go into components of candidate portfolio and some stochastic methodology. And then Devin will discuss scenario and sensitivity results. And then I'll finish off with our 2 to 4 year action plan, and then the remaining timeline. So with that said, we'll go through introductions. I'll just go down this list. So if I say your name, please introduce yourself and your the company you're representing and your role. Abe.
Hi, this is Abe Abdallah, Utility Analyst, Oregon Public Utility Commission.
Thanks, Abe. Pam.
Pam Archer, Regulatory Analyst, Cascade.
Thanks, Pam. JP.
This is JP Botmall with the Oregon Public Utility Commission.
Thanks, JP. Bruce.
Good morning, Bruce Folsom, independent consultant, working with Cascade on their IRP.
Thanks, Bruce. Kathleen.
Hey there, Kathleen Campbell, Senior Engineer with Montana Dakota's Utilities Group.
Thanks, Kathleen. Kevin.
Good morning, Kevin Connell, Director of Gas Supply for Cascade Natural Gas.
Monica.
Good morning, Monica Kalasha, manage Cascade's energy efficiency program, primarily Washington.
Thanks, Monica. Ashton.
Good morning, everybody. Ashton Michael Davis here, economist with Cascade.
Thanks, Ashton. Kim.
Hi, folks. Kim Herb with Oregon Public Utility Commission.
Thanks, Kim. Hai Xiao.
Good morning, everyone. My name is Hai Xiao Huang, economist, strategic planning with Northwestern Natural. Thank you.
Thank you. Kathy.
Kathy Moyd, following for League of Women Voters. I'm probably going to be in and out. I'm mostly interested in when you start getting into the portfolios.
Okay.
I don't really have much expertise in all the detailed areas.
Yep. Thanks, Kathy. Mark.
Good morning. This is Mark Sellers Vaughn, a manager supply resource planning with Cascade. I also handle some upstream pipeline relations.
Thanks, Mark. Devin.
Hey, good morning, everyone. Devin McGreal, Senior Resource Planning Economist with Cascade. Thanks for coming.
Thanks. Mike.
Mike Parvinen with Regulatory Affairs, Cascade.
Thanks, Mike. Caleb.
Yeah, good morning. Caleb Reimer, Economic Analyst with Cascade.
Thanks, Caleb. Zach.
Yeah, Zach Sowards, Engineer with Engineering Services with MDU.
Thanks, Zach. Carolyn.
Carolyn Stone with Cascade Natural Gas and Gas Supply.
And Sebastian.
Yeah, hey, Sebastian Weber, representing Northwest Natural. I'm on the strategic planning team there.
Thank you. And did anyone else join while we were going through introductions? I don't see any other names, but. All right. Okay, we'll keep going. Are there any questions before we get going? Oh, Daniel. I see your camera popped on. If you are speaking, you are on mute.
No questions, just joining the meeting. Thank you.
Okay, thank you. All right, so quick safety moment. I know that towards the end of the IRP process, it can be pretty stressful. A lot of narrative to put together. I'm sure we'll get a lot of information requests, and we'll do our best to get those done. But in the meantime, if you're feeling stressed from work, from outside of work, here's a couple of tips. Listen to music. Playing calm, meditative, relaxing music can help lower blood pressure. Talk to someone, a friend, a counselor. Mental health is very important, so take care of yourself. Healthy eating. Try to avoid sugary food. I know we just had Halloween, so don't be digging through your kids' candy like I am. So make sure you stick to healthy eating. Laughter is very good, so get together with friends, go to a comedy club. Laughing is very, very good for you. Drinking tea, avoid coffee and caffeinated drinks. So try to stick to drinking tea. Water is also very good for you. Exercise. Whenever you're at work and you have 10 minutes, take a quick walk. After work, if you can exercise for 20-30 minutes, that'll go a long way to helping relieve stress. And then make sure you breathe. So take slow, deep breaths to center your body and clear your mind and slow your heart rate. So I want to touch on the stakeholder engagement document. We have that out on our Oregon IRP website. You can go out there. We have our IRP timeline. You can check out videos from our last 4 tag meetings. The presentations are out there as well. But I want to touch on the goals of the stakeholder engagement document. While Cascade owns and is responsible for the IRP, the company desires to have involvement from stakeholders to provide a diversity of perspectives. A best practice IRP is informed by perspectives, analysis, and access to concerns and approaches that the company may not have considered. And some stakeholders participate in multiple IRP processes. We also participate in other LDCs, other regional LDCs, Vista, Northwest Natural, PSE. But you guys may have a line of sight on something that we may not be considering. You may have had conversations offline with these LDCs. If you bring those to us to consider, that's very helpful. So putting together an IRP, it is Cascade's document, but we appreciate any considerations or thoughts we can get from external members as well. With that said, I'm going to pass it over to Kathleen. I think Kathleen, you're going to share your screen.
Yep, I'll get set up.
Okay.
Trying to get set up better so I can see comments. So trying something new. But yeah, I think I'm ready. So yeah, so today I'll be covering distribution system planning. I'm Kathleen Campbell, I'm a senior engineer in our engineering services team for Montana Dakota's utilities groups. This presentation will be for Oregon. It'll be very similar to the presentation I gave in Washington Tag 4. the beginning at least, but it'll cover Oregon specific projects. So we can get started. So presentation wise, I'll just let you guys know this is going to run about just under 45 minutes is what I expect. And then we'll open it up to questions. But feel free, as always, we didn't go over this yet, but you can interrupt or ask questions as we go. And I can go back on slides as needed. So this presentation is going to cover our distribution system modeling process, identification of system deficits and constraints, distribution enhancements and reinforcement options to address those deficits, how enhancements are reviewed and selected to our capital budget. I'm also going to cover enhancements and reinforcements that are in our 5-year budget, so 2023 to 2027. And then lastly, to kind of close up, I'm going to cover some changing dynamics and the iterative process of the IRP. Get started, I'm going to first cover distribution system modeling. So just system dynamics and a little background to get you familiarized with our system before we begin. So Cascade operates a diverse range of pipeline diameters and operating pressures. And as you can see for Oregon, we operate about 1,700 miles of distribution and 107 miles of transmission. System dynamics, in addition to piping, we also have facilities on our distribution system, several regulator station, valves, and other equipment such as heaters, odorizers, and compressors. So next up, since we're going to be talking distribution system planning, I wanted to give you a very high level introduction to our systems and kind of how they work. So all of Cascade systems are served by these green pipelines, which are interstate pipelines. This would be Williams and TransCanada pipelines. Off those, we have gate stations. At a gate station, that is where Cascade takes over regulation and odorizes the gas. Typically, gate stations serve high pressure and transmission laterals. Off those laterals, we can have industrial customers. Some of them have delivery pressures, etc. And then they also feed our regulator stations. Our regulator stations typically cut pressure down to distribution pressure, and then they feed our distribution system. Off the distribution system, we typically have our residential and commercial customers. So that's just high level overview of what we're talking about in our system. So high pressure laterals, distribution systems, gate stations. So all this and kind of the base of a lot of our distribution system planning comes from our synergy modeling. We use Synergy to evaluate our systems for growth and potential deficits. Synergy Gas is a software program. It's distributed and supported by DNLVGL. And basically our Synergy models incorporate all of our customer loads and all of our existing pipe and system configurations. In a nutshell, what Synergy is, it's basically a hydraulic modeling software that allows us to predict flows and pressures on our system based on gas demands predicted during a peak weather event. For Cascade, our models are updated every 3 years, and then they are maintained between the rebuilds. So this is just a Synergy model example. So this is a screenshot from GIS. You can see this is our piping in GIS where it's at, and then we use this to bring into Synergy. So this is basically that system as a Synergy model in Synergy. So in Synergy we have it's just super high level, but circles are sources, so that would be gates. You can see these little triangles or little reg stations, and then you kind of lets you see the high pressure line. So you can see this is actually Tri-Cities. So this is Pasco, Kennewick, Richland. This is the Italia lateral that runs down to a large volume customer. So you can just kind of see how that gets built and how realistic our Synergy models are to our GIS data. So, and then just a brief snapshot. So like I mentioned, all of our distribution systems are unique in their customer served and in their pipeline characteristics. So next up, I'd like to cover our model building process. So like I mentioned, models are rebuilt every 3 years and then they're maintained. So we want all of our Synergy models, drive a lot of our operations decisions. So we have to keep them updated and maintained so we can, effectively manage our systems. So when the models are rebuilt, we export in new GIS data to build the spatial model. So whatever pipe's been installed, it's all been captured. that comes in and we completely rebuild the models. We also export all the current CCMB billing data. And that process goes through a synergy model called CMM, which is Customer Management Module. And this helps us create an updated demand file. So completely rebuilt models every 3 years. And then we go through a process where we validate and calibrate each district model to a recent low pressure event, using actual data. So we dial in these models, we get our PRX data, pressure chart data, SCADA data, large volume usage, Metrotech data to make sure the models are, the rebuilt models are accurate and representing our system, on a previous day. We want to see like pressures and things be accurate. Typically, a best practice for model building is for models to be on this day that we validate them. We typically want a best practice is being within 10% of actual data. So we'd want to see pressure charts and things that let us monitor our system, accurately re-represent that event. We also create, so the design day models are updated. So once we, and I'm going to go over this in some more slides, but just high level. So once we calibrate a model, that kind of means we accept it. We know it's oh, I got a hand that popped up. Go ahead.
Hey, Kathleen, thanks. So just real quick, when you guys say the models were rebuilt in 2021, so that's so just I'm trying to make sure I understand. So the model says this is what's going to happen, and then you go out and actually put monitors out in the field and calibrate that to make sure that that's actually what you're seeing on given like design day events. Is that right? And then if there's a variation, then you go back and rejigger the model.
Yeah, so we make sure when it's rebuilt, there might be piping that was replaced because we try to maintain them, between the 3-year rebuilds. But when they're rebuilt, we know that that's like the best data we have. So they're actually better models in that like anything that's been replaced, if pipe replacement's got in there, or system integrity, or anything that's been replaced in the system, maybe a cutout, anything with the pipe. So we know we have like accurate pipe data, and then we recalibrate it. And then I'm going to talk about it, but then we ramp it up to the design day. So the calibration is just a specific day to make sure the rebuild was effective. Make sure we can kind of trust the model. Does that make sense for you? Okay. Got a thumbs up from JP. That's good. Yeah, and so I'll get into that, and I have some more slides. So I think that's just what I wanted to cover on this one. And then, like I talked about, JP, so that design day model is determined by that peak gas usage, which is given to us by regulatory, which is our historical low weather event. And a while back, it was that 30 years. So they trend weather back. So when we calibrate the model, this is just one thing I'll point out a little bit. We calibrate to the coldest day in the 3 years, because that's just the best data we have that's been recent. And then that helps us accept the model. And then we ramp it up to that, the lowest cold temperature we predict could happen for the area, which I think is on the next slide. So we'll get there, but yeah, just a couple things with just rebuilding these models. I have a couple screenshots. So this is just data gathering. So this is CCMB data. This is just customer usage. So also with the model, in those 3 years, we're getting updated customer usage, whatever's gone on in their billing data, updated usage. And then also with that, I got a SCADA screenshot. So this is some real-time historical flows on our system. So we have SCADA at several gates and at large volume customers and critical points on our system. So we have live data and historical data we can go and pull to check our models. Data gathering. So this is, yeah.
Hey, Kathleen, I think we have a question from Abe.
Okay, sure. Hope I can't hear you, Abe.
Hello, can you hear
There
me?
you go. I can.
Yeah, sorry, I had to use the microphone here. Thanks for your explanation. I just wanted to know if the choice of 3 years is the most sort of effective, and it's actually a bunch of questions. And what happens when you have some system changes during those 3 years? And also, is one the lowest event, is that enough to validate and calibrate the model accurately? So it's basically 3 questions
Yeah.
I have. Yeah.
Yeah, so I'll take your first one. So with calibration, I do think anytime you can calibrate and go into your coldest, temperature you experienced over 3 years, I do think that's accurate because you are like replicating your system. So if you can get them within that 10% threshold, or some of our models perform higher than that, I do think that's acceptable and kind of industry standard. And then your other question on the 3-year rebuilds, the 3-year rebuilds actually for Cascade is more frequently than they used to be built. So we've actually made improvements and we've staffed. One of our engineers, Zach's on here, does our model builds. But yeah, that has been an improvement for Cascade. And I think personally 3 years is a good interval. And it's just how we go through. So we rebuild in our group, we rebuild Cascade, Intermountain, and MDU. So we're on the 3-year cycle because we do one each year. So that's just our rotation in engineering services. So a little more insight for you there. And then your third question, can you?
What if you have system change, physical system changes? What happens during those 3 years?
Yeah, so with our synergy models, we have engineers that are assigned to each district. Each district, each engineer handles 2 to 3 districts in our service territory, and those engineers are responsible to keep the model updated. So if there's pipe or capital projects installed, or even large customer requests, we input all that in the model. So we do try to keep them updated as we go through the 3 years as best we can. And there's checks they do in engineering services. So yeah, the goal is to have keep the models up to date. But yeah.
Thanks.
Yeah. Problem. Okay, I'll continue on. So with data gathering, I wanted to talk a little bit about our peak heating degree day. I also call this our design heating degree day. So they're kind of interchangeable, but what this is based on is a 60-degree temperature. And I'm sure everyone knows, we've gone over this, but in Oregon and Washington, when the temperature gets below 60 degrees, customers turn their heat on. That's kind of the threshold. So basically, you take 60 minus your average daily temperature, and that gets you your heating degree day. So if the temperature is 59, your heating degree day is 1. So that's kind of how it works. So any day you could have a heating degree day, every day does. And you can calculate it based on the temperature. But for us, the peak heating degree days is those 30-year trending historical lows for the areas. And we break our models up by district, because you can see we operate through a diverse region. You can see coastal and you can see some desert out in Tri-Cities where I live. So just different dynamics. So we have to break them down, and we get a design heating degree day for each area, which is what this is. And you can take these temperatures and convert them using this equation into what that temperature is, that average daily temperature is in Fahrenheit. So for instance, Ben, its heating degree day is 71, which corresponds to a minus 11 average daily temperature. So to get the average daily temperature, you just take the min and the max temperature, and that'll get you that. And so you can always, any day of the year, you can get a heating degree day, take the average, and then use this equation. So that's where we're at. So you can kind of see like our, a little bit of our diversity and why we break it down. So I'll keep going. So this is CMM. This is our customer management module, just a screenshot. So this is kind of what I talked about in Synergy. So we use CMM takes in our CC&B billing data, and we bring it into CMM, and it helps us create the demands file. It helps us predict usage per customer. And then another thing CMM does is it works to apply the demands file spatially in the model.
Hey, Kathleen, we have another question.
Okay, sure.
Kathleen?
Yeah, I guess this is probably very late in the process, but people don't turn their heat on until it gets all the way down to 60.
That's what we've seen, yeah, in Oregon and Washington. I will let you know, like in Idaho, we use 65, but it's I think they've done regulatory, and Brian would know more on this, but yeah, 60.
Yeah, so
Everybody's different. Yeah.
So we did an analysis and we looked at our data, and it's not really that customers are turning on their heat, it's just that furnaces are used very little between 60 and 65 degrees, just because homes have become much more efficient at keeping heat inside the house, that it takes temperatures below 60 for the house to start cooling down inside, where the furnaces would start kicking on.
Okay, that makes more sense. Because
yeah,
I know
it varies quite a bit based on your region and location. We serve Western Washington, where temperatures don't get above 70 very often, but we also serve Central Oregon or Eastern Oregon and Central Washington, where temperatures will get pretty high and pretty low. So it kind of varies, but we've noticed on our system 60 is about where usage starts going up.
Okay, thank you. I was just curious.
I'll continue. So this is kind of what we've been building on, or what we've been talking about. So what this is going to show is, so as that degree day gets colder, what we've been talking about, so the degree day is increasing, so temps are getting colder and people's usage is going up. And that's really what CMM helps us get, is it helps us get this linear regression, this line with this equation on how to predict, if it's this cold, it's this much usage. It's a linear relationship. So next I'll show you. So I got a couple, this slide progresses a little bit. So this is kind of our calibrated design day. So this is over that 3 years, we want the coldest day we can get to check the model. So that's where this comes in. And then once we get this linear regression, then this allows us to I guess, predict our design day usage. So that's where we get our peak design day. And that's what we build the models to. So this is what we build, and when we start getting into deficits and things, this is what we're using, the peak design day, which is the coldest weather we, expect to see, to make sure our systems can sustain those temperatures. And next up, so that kind of wraps up our model building process. So next up, I'm going to move into identification of system deficits and constraints. So with this, we've kind of been talking about synergy modeling, but I just wanted to go over all the things. So we spend a lot of time and money like building our synergy models. And the reason why is we use our synergy models for a lot of our engineering. So with our synergy models, once we have these built, we do that 3-year, calibrate it, ramp it up. We use the design day models to look at all of our large customer requests, model our renewable natural gas. It supports design and sizing of our pipe and pipeline components. Lets us do future planning, lets us model IRP predicted growth, helps us to identify deficiencies, helps us with system reliability, helps us optimize our distribution enhancement options. So when we compare reinforcements to each other, they're all modeled in synergy. And then it also helps us with our cold weather action plans and modeling curtailments and interruptible customers. So next up, I'd just like to cover what a capacity deficit is. Deficit is defined as a critical system that is at or limiting capacity. So some examples of capacity deficits include pipeline bottlenecks, minimum inlet pressures to a reg stations or high pressure system, not meeting a required customer delivery pressure, or a component limiting capacity. So to expand on capacity limiting, I wanted to explain a little bit on minimum inlet pressures, on a high pressure system. So let's say I have a 500-pound high pressure system, and it's going to serve a 200-pound distribution system. So 500. So if my 500-pound system at where it needs to cut to 200 pounds, if that line is down below 200 pounds, it's compromised. It can't provide the full pressure to the 200-pound system. So that's just an example of a high pressure system that would be identified as a deficit. It can't meet its required delivery pressure. It could also be a high pressure line that is cutting to distribution system. So if at the end of my high pressure line I can't cut to 60 pounds, that would also be a deficit because it's compromising the downstream system. So that's just kind of an example of not meeting a required delivery pressure. Not meeting a required customer delivery pressure is that we have Cascade has several large volume customers that have delivery pressure requirements per their contracts. So an example of this is PSC Fredonia, one of the cogens out in Anacortes area, off of Fredonia transmission system. They have a minimum delivery pressure of 305. So if that high pressure system can't meet 305, we're not meeting our contract for that customer. So that could be a potential deficit if that was to occur. Continue. So just with our I want to cover distribution system modeling process and how we do that to make sure we can meet growth. So as part of the IRP process, we do a comprehensive review of all of our distribution systems every 2 years to make sure that we can maintain reliable service to our customers during peak low temperature events. So that's those design day events we talked about. And then also with our budget, we also do reviews annually just with our budget cycle. Typically we budget in June or July, and we also kind of recheck systems. So if we find a deficit, if it's predicted, we'll evaluate it and propose a reinforcement or enhancement. And then by proposing that, we typically go through an alternative analysis where we're comparing options and go through selection, which I'm going to cover in the next section. And then those reinforcements or enhancements that are needed for the deficit will be placed into the capital budget based on timing when we predict the deficit will occur. So next, I'm going to cover our distribution enhancement and reinforcement options to address deficits. So like I said, we review systems, find deficits, and I'm going to go through kind of how we look at options for those. So enhancement options, I'll just cover this at a high level, but for pipelines, we can replace pipelines. Pipeline could be replaced and operated at a higher pressure, or it could just be replaced with a larger size pipe. Pipelines can be reinforced, so maybe a backfeed or loop is put in. Other options is you can always do pressure increases on lines, or you could uprate a line. So anytime a line can operate at a higher pressure, it can get more capacity down the line. Other enhancements would be facility upgrades, so gate upgrades, reg upgrades, compressor upgrades, things like that. For distribution systems, some enhancement options would be adding reg stations to a system, because reg stations provide a fresh pressure source and will provide a redundant feed. Other options is you could also add gate stations to systems. So strategically placed gate stations can also help systems and help high pressure systems. Last option I have on here is compressor stations. So compressor stations boost pressure down laterals. So now just to kind of cover, I was going to go through a distribution enhancement example. So this is kind of like something one of our engineers might work through. So in this system, I got pressures on here, and it's just a little town. At a high level glance, I'll just give you a little insight, but this is the gate. So this is the source off the pipeline. And it looks like I can see my regs. So these are regs. Looks like we have 5 reg stations. So I can, there's high pressure that kind of runs through here. And then this is mainly the distribution system. So in this system, we have an area that's, you know, kind of on the southeast section is under 10 pounds. So, you know, we could identify this as a deficit and then, you know, work through how we'd fix this system. You know, what options do we have and what would we select? So with this,
Kathleen, it looks like we have a question.
okay, sure.
JP?
Yeah, my computer's super slow all of a sudden. I don't know why. Sorry.
No problem.
My apologies. Hey, Kathleen, do you want to finish this or should we ask, can I ask questions now about like at what point in the enhancement process do alternatives get looked at?
I'm going to cover that.
Okay.
Yeah, so I'm actually going to cover that. So why don't you check back in?
Yep, that's fine.
And yeah, we'll go through that process. I'm going to cover that whole process on how we go about all alternative analysis. Okay, I'll keep going. So this one. So I guess this was just options. You know, someone threw out a compressor, but oh, I guess I have to click. So this side progresses. So here's some regs. So that could be an option. We could, you know, so with so just high level enhancement options, you could always run pipes. I see there's some you know, this pipe's kind of isolated. And currently it looks like it's kind of fed one way, maybe 2 ways. Not currently fed, you know, the third way. So that could be an option. You can always run on distribution systems. You can always run like larger main out of the regs. This could be a potential solution, or pipe loops. So regs are pointed out. Here's pipe, couple options. You know, and we'd go through like which one's the best option. So with this, this one looked really good. This example, you know, things that look good in synergy. You know, we always got to check feasibility and construction. So this one actually turned out to be in the middle of an airport. So, you know, as we went through alternative analysis, we were to go through kind of what we showed, you know, trunk lines out of regs or piping, you know, this option could be eliminated because we can't put pipe through the middle of an airport. So it's the X. And then this one, you know, as we work through this, you know, this is high level, so pretty simple. But yeah, so you choose. So in this one, they went through alternative analysis and they chose this this pipe loop down on the south end. And this shows pressures after the loop's completed. So it got us over 10 pounds, which is what our goal was. So it was acceptable reinforcement. So, you know, every solution is unique and could be, you know, we need to think about feasibility. And that's some of the stuff we'll talk about with alternatives and how we go about that. But, you know, just a note on this, you know, our goal really was just getting us over 10 pounds. You know, we don't want to overbuild, or we definitely could have done a lot more to this system. But we don't want to overbuild. We just want to get the growth that's occurring, you know, that's currently a deficit, because, you know, deficits are going to change, you know, different areas. We're going to have deficits at different times. So we don't want to overbuild. And, you know, we think about this systems, there could be something that's limiting growth. Maybe this is all farmland and it would never, maybe the growth that's been happening down in this southeast, you know, is going to get constrained at some point, or maybe there's a lake or something else going on where you couldn't get more growth this way. So just things to think about, and kind of a high level example how we work through, you know, identify deficits and then work through solutions. So when we look at enhancements, these are some of our considerations that we look at on every project. We look at scope, cost, capacity increase, timing, system benefits, alternative analysis, and feasibility. So each enhancement, like I said on the last example, would have pros and cons, and we weigh them out in the alternative analysis, you know, before it is selected. And several factors can play into what's selected. You know, like I said, permitting could be one. Like, you know, we might not be able to put a compressor in the middle of a city. You know, different things would make some enhancement. Maybe, you know, we'd eliminate those options. So with this, I actually want to introduce a new one we're looking at. So with our alternative analysis, one thing we are considering as an extra alternative for us is demand side management. We're actually kicking off a pilot program. So we are working with Energy Trust Oregon to develop a pilot program for both Baker City and Ontario. We're going to attempt to do targeted demand side management to offset growth demand increases predicted, to see if we can avoid proposed reinforcements for those towns. We've determined that Baker City and Ontario are both good candidates because we've had time to identify the deficit and get DSM in place, so we can see the impact. So there's enough time, and that's kind of the trick. So we've had a couple meetings with Energy Trust of Oregon, and they're kind of recommending 3 to 5 years to be able to get a program in place and to be able to see if it's effective. With this, it's kind of new and exciting, but the pilot program, we're going to see how it goes. But if it does not offset enough load for the reinforcement, at that time we may still need to complete the reinforcement. So kind of a new thing that we're bringing into this IRP and bringing into our alternative analysis as an option to address deficits. So now I think this is going to kind of cover what you're looking for, CP, but I'm going to talk about our enhancement review and then how we select projects to the capital budget. Thought I saw a hand flash, but it might have just got pulled down. Someone have something?
Yeah, this is Abe. I just wanted to know, just on the high level, demand side management is only targeting commercial and industrial, or also residential?
I believe it's going to be all the above.
Yeah. Okay, thanks.
Yeah, and some of that's going to be Energy Trust Oregon. So as I understand, they're like going to give us a proposal because we kind of have like a load reduction we want, and then they'll come back to us on what to target, I guess. But yeah, I see Jason or JP.
Hey, thanks, Kathleen. In terms of the timing and the selection of alternatives, how do you see that process playing out? So as you guys are running Synergy and you're looking and something's either emerging or does emerge, at what point in your process are you guys now thinking about looking at alternatives? Whether it's DSM, whether it's looking at interruptible loads. Can you describe that portion of your process?
Yeah, I haven't.
And then I guess
haven't quite
the
got
second
there
part of
yet.
that is how proactive can you guys be about that? Thanks.
Yeah. Yeah, so I'm going to get there because we're going to talk about like how we go through our budgeting. But yeah, I got a slide that's going to kind of break it out. It's like
Jumping the
blocks.
gun, sorry.
No, it's okay. But yeah, so the proactiveness, I can address that, but it'll depend on if there's time. So if there's urgent need for a reinforcement, there might not be time. So you wouldn't, there are a couple, and as we go through our capital projects, there's a couple we've thrown out DSM on. So we considered it, but it's urgent need. So it's kind of like for DSM, there has to be kind of that time. You need that 3 to 5 years to get it implemented, and for those upgrades to be made, to the homes, those energy efficiency programs to get constructed and put into the houses, and then seen in our load data. But yeah, I'll keep going. So I'm going to get to where you. But yeah, so our enhancement selection guidelines, just high level. This is how we look at them and how we pick them. So we always want the shortest segment of pipe that addresses the deficiency. Kind of like I talked about on that example, is not overbuilding. We want the most favorable construction conditions for a pipeline. So things, and that could impact costs. So if there's opportunity to go on a new, and maybe a new road's going in and we wouldn't have any restoration, that would be favorable or could be outweighed to another option. We typically want to minimize environmental concerns and impacts to the community. So when we're looking at our pipeline routes, kind of like that airport example we did, but if it has water crossings or going through wetlands, we maybe want to avoid those. Impacts to the community, just to expand on that, an example of that would be if there's a road moratorium. So if they, the city, let's say they just upgraded this road, they made it 5 lanes, put curb and sidewalk in, it's, we might choose an alternative route than going down that road. And it could also be cost driven. So sometimes restoration on, recently upgraded roads is very high. You got to pave the whole 5 lanes, and they really, some of the moratoriums the city put on really deter you from those routes. So maybe you have to go like a little bit longer route, for the same, to address the deficit. We'd also maybe look at opportunities to provide additional customers. So when we look at looping and things, sometimes, if we already have main down the road, and we're serving customers, maybe running another road, or maybe there's opportunity to get more customers on or put gas in a new area. So that could be another consideration. Always looking at construction cost, including restoration, and then looking at demand side management. If, we typically model out if the load reduction will eliminate the need for the reinforcement. So we do a little due diligence on modeling before, to see if it's effective or if it's potential, and if we have that time. I see one from Kim.
Hi, thanks. When you have the analysis of this opportunity to add additional customers, what level of sort of further future, I'd say, compliance costs get captured with that? So, assuming each new customer brings with it new climate protection program compliance obligations, is that additional cost captured in this evaluation?
I'd have to look, or I'm not sure what those costs would be. I mean, are you talking like maintenance, like because we have made in a new area, like leak survey and things, or is this like emissions
No,
related?
I mean that, with each new customer served, that's essentially additional load that has to meet the emission reductions, and in recognizing that there's an upward trajectory in what that cost might look like, and how that affects all customers. I guess I'm wondering if that additional load and the emissions associated with those loads, and then the costs associated with reducing those emissions, are captured in this particular evaluation.
In my experience, when we typically run, or when you run, if there's existing homes or they're pretty well built out, you don't usually pick up too many customers. They usually already have their, their electric, or there's some reason that they haven't been on gas. Typically, you'll just get a couple service lines. I would say it's pretty minimal on what we can add. I guess it just provides that opportunity that maybe they'd go gas, or like do a gas fireplace or something, but it's usually not that significant of a load increase in what I've seen. But yeah, we might have to get back on that one. It's typically not part of engineering's review, though. An alternative analysis. Yeah. So yeah, so this is the block. So yeah, this is, I think, what CP is looking for. So we'll talk through this a little bit, but with our enhancement selection process, kind of what we've been building up on. So we take all of our IRP growth, our design day models, and then our district info. We have things on like housing developments or city developments, road upgrades, moratoriums, all the things I talked about. We take all that in, and we assess, if we have any system limitations or system deficits. Typically that's done by our engineers during budgeting. We do a more thorough review on the 2-year IRP cycles. Once we identify those deficits, then we kind of go into our alternative analysis. So we identify projects to fix the deficits, and then go through alternative analysis. So, and then with that, kind of benefit, feasibility, and costs kind of built in. And once we get that, we typically, a lot of engineers will kind of work with their managers. So a lot of this, our engineers will model, identify the deficits, and then they'll kind of proactively work with management on, making sure all the alternatives are there. I work a little bit with engineers too, and we get to this process on checking, making sure we're not missing a potential alternative. And then once that happens, we'll pick projects for the capital budget, and then they'll get ranked. So our projects will go based on cost, feasibility costs. So this has to do with like timing and when we need to do the project. We'll kind of accept projects we're going to do that are needed, and then we get them scheduled into the budget. And then with this, every year, I guess I'll kind of mention, but with the IRP, we'll make tweaks as needed annually. So, we're also like re-reviewing projects that, we've put in the 5-year budget, and with the IRP, this process kind of flows through every year. So things could get moved or changed as needed based on timing. And typically right now, I'll just give you a little bit of insight. So we are in our capital budget process. We don't have an approved 2023 budget. So projects I'm presenting on today are in our 5-year budget. They just haven't been accepted. So for Cascade, what happens is I think it's in July, we do our first pass of the capital budget, and then the budget goes through 3 or 4 or 5 revisions. So I think we're probably on the last revision, and then it typically gets approved by the executives around Thanksgiving. So likely this month we'll have the approved 2023 budget.
Hey, Kathleen.
Yeah.
Hey, just kind of building on Kim's comment. At what point in your kind of budgeting cost feasibility process here, because this is really helpful. At what point does the engineering team take in constraints around emissions, given like what's happening with CPP? How does that play into the analysis I think for a casual observer, where you see growth in another part of the system, there needs to be some sort of balance on another part of the system. How does that play into the analysis here?
Well, it's really just the deficits we're predicting out with growth. So if we have CCP goals or whatever our growth predictions are, so when we look at that 5 years, some of those numbers we're looking at growth, could include CPP, but our CPP program's kind of a little bit separate process, because I know they can buy credits, or there's other opportunities. I know Abby might be on here, but I know they have a plan for CPP. It's kind of independent of capital projects. Correct me if I'm wrong, or feel free others chime in here.
Hey, Kathleen, I'll just jump in real quick. And as part of our portfolio modeling, we do model some general growth. And so as long as the customers, if it's under general growth and we feel comfortable that we can meet the CPP targets, we will go ahead and add them on our distribution system plan. We have had, and I'm not going to throw any names out there, we have had a large industrial customer in Oregon come to us and ask if they can come onto our system. And we worked with business development, engineering, and environmental policy, and we determined that their increase of load would put us in a really bad position for CPP. And so as of right now, there are no plans to add that customer to our system. So when we're looking at smaller customers, residential, industrial, commercial, just business as usual, we've continued to add them, but there are discussions internally about what to do about these large customers who may increase our carbon compliance targets, or our carbon footprint, and put us in a bad position to meet carbon compliance targets. Is that helpful at all?
Yeah, kind of. I think maybe the next question, my follow-up question, and then I'll turn over to everybody else. Brian, is for you. Given what Kathleen's laid out, and that they have a routinized process, where by Thanksgiving, things that they've been looking at for a while come to capital budget approval based on the criteria she's laying out. how soon in the IRP process are you all made aware of what they're considering so that you can begin talking about alternatives and exploring alternatives before they get to the budget process? It seems like there might, just from what I'm hearing, it seems like there might be a disconnect between the engineering budgeting process versus the compliance process. And so I'm wondering, like, in your planning, how soon are you guys being made aware of, and then how soon can alternatives be explored insofar as we're looking at an expansion of the system, kind of, bringing risks, right? So like, and not risk that Kathleen's thinking of, but rather risk, of costs being out there that need to be serviced and bring on, potentially even fines. So maybe you can explain that, because I'm understanding kind of better what Kathleen has to go through and their team, but insofar as it seemed like if CPP is truly a separate part of the process for them, then how soon are you all being made aware of it by engineering of what they're thinking about in their budget and capital improvement process, so that alternatives can be considered, prior to them giving it a stamp and then being caught unawares that, where the PUC is opposed.
JP, this is Devin. So one thing I'll just kind of chime in on that a little bit is just kind of one perspective on it. When Kathleen and our engineering team are kind of making these decisions about where we're going to need some of these reinforcements, specifically on that growth side, one thing that we're all doing is using a unified kind of projection on what load growth will be, right? So Kathleen's not, or the entire engineering team, they're not necessarily talking about projects that we're not already considering on the IRP side or the resource planning side. We're oftentimes looking at the same thing. So for instance, an investment in a system reinforcement in Bend, for instance, that may, end up costing X number of dollars, and because they're seeing 1% growth in a certain area that they're going to need to reinforce their system, we would presumably be accounting for that same growth because it's a similar load forecast, right? We're looking at the same factors that are projecting out our load forecast. So we're going to be accounting for that already. I don't think there are going to be oftentimes, because the other thing is these large industrial customers, and then we do have processes with our industrial services folks where we're all working uniformly on those kind of one-off situations. But many of the reinforcements that this process is talking about related to growth are things that we're all looking at kind of homogeneously. So I don't think there's any kind of necessarily conflicting or siloed approach to this. I think the fact that it's all kind of going on the same growth projections mean we are accounting for the same things that they are in these processes.
Yeah, but I mean, we can, and I don't want to high center on this, we can have an offline conversation, but what I'm hearing you say and then what I'm hearing Kathleen say are not totally separate things, but there is a gap there insofar as CPP compliance is a bit of a separate process. That's not, that doesn't speak to me of a holistic process to consider the risk and how to avoid, expensive emissions growth, right?
Sure. Yeah. Let me think on this some more. Because I agree.
thanks.
I think I want to come up with a better holistic answer for you on that. But I think my initial gut reaction is that it is something that's being kind of looked at holistically. But let me think about this some more and come up with a more unified response for you.
Yeah, and I got a little bit. So a lot of the growth we're looking at is core. So we get the numbers from like Brian's group on core growth behind gates. And that core growth behind the gates includes the CPP. So it's already accounted for by the time I get it. So when I'm looking at system limitations or deficits, I do those growth for gates. And there's some gates that don't have any growth predicted. So I just that's what engineering dials into the models for the IRP. So it's just core growth, and it has nothing to do with industrial customers. That's a separate process. Each industrial customer is evaluated separate, and it's they have to pay for their reinforcements. Yeah, I got to see another hand up.
Yeah, this is Abe again. Sorry. Is someone else, or was that only me?
Yeah, I see Daniel had his hand up first. I don't know if we want to go to Daniel.
Yeah, go ahead, Daniel.
I'm a novice here, so looking forward to hearing your question. Following up on this, I was just wondering how the distribution planning informs bigger transport supply questions. And I'm thinking specifically of the GTN Express project, which is a pretty big chunk of gas, and whether that's built into costs at the distribution level or not. I'm wondering how they work together or not at all. So that may be a question for later. Thanks.
No, we can take them as we go. So this, our budgeting or distribution system planning is just our systems. So anything downstream of our gates, our, our regulatory group or gas supply and some others, they deal with gas supply. So that would be like more like GTN or whoever we're buying gas from. And you guys can speak up too. I know I'm a little detached from that gas supply side.
Yeah, I wouldn't be able to speak on the GTN Express and how it impacts distribution system planning. I do know that we are looking at picking up 20,000 decatherms. Well, we contracted, we've agreed to it later in 2023, because if we don't pick up the 20,000, we would be short serving customers in Central Oregon if a peak day hit. And so we incorporate those costs in our upstream modeling. Now, I'm not sure how that ties to the distribution system planning process.
It ties a little bit. So when we upgrade the gates, if we're asking for more capacity on a gate, so if we're upgrading, and we do have a couple gate upgrades, TransCanada has to have the capacity to upgrade it or to give us that higher therms per day.
Thank you. That helps to answer it.
Mm-hmm. Okay. See another one, I think.
Yeah, this is Abe again. Just going back to the emission requirements, the compliance. How easy is it to integrate or to add the emissions from each solution that you get? If you have a base emissions, for example, and then you're trying different solutions, how easy is it to integrate that with calculation for emissions? And because that's got a cost at the end of the day. So is that something that can be done?
It's a good question. The CPP is kind of new. These are going to be things we're going to have to be like considering. So it's good input for the IRP. I don't think I have a good answer at this time for you.
Thank you.
Abe, can you repeat the question?
He wants to know like costs. So it's if you're comparing reinforcements, I guess, on your costs on your emissions, right? Your long term. Is that kind of what you're asking for, Abe? How you compare?
Yeah, I didn't mean dollars necessarily, but we can convert that to dollars later, but at least see the emission impact of each solution, and how's that going to translate eventually to cost, I guess. But it does help probably to see how we impact, how the solutions impact the emission requirements. And I guess you said things about operating, and they would have different costs probably depending on the amount of molecules used, I guess. And I don't know, do you get the feel of, would they vary, the solutions will vary with their impact, or will be more or less the same with residential? You mentioned the industrial is a different sort of kettle of fish, but this one is, I just wanted to have a feel, of how different solutions will impact the emissions.
I don't know if the solutions would. So when we get the gate, or if we're predicting growth behind a gate, it's already built in. The CCP strategy is kind of already baked in by the time we get it. So like those enhancements, we'd still have the same gate flow that's predicted. It's just how your alternatives, how I'm getting it out in my system would just change a little bit with the alternatives. The town would still use the same amount of gas, which is those, I guess, how we did it is it's in the gate prediction. So I get like so many therms per gate, for the, I think we have it out 10 or even 30 years. And then we add, like the engineers, we put those in the model and then we look for the deficits. So I don't know if it would come into play on alternative analysis, because it would just be like how it's flowing in the system, the distribution, is it it's a high pressure upgrade? And I don't know I don't think the molecules will change between enhancement solutions, but it's just a good discussion, things to think about. The CPP is new and we'll have to think about these going forward.
Yeah, I guess the demand side management solutions will tend to reduce those emissions, or RNG or any others non-pipe solution. So it might be just a metric that we want to look at.
Yeah, no,
I got a slide at the end you're gonna like, but we're gonna talk about some of that to kind of wrap up. But yeah, you're right. And
Kathleen,
how those things change.
Thank you.
Yeah.
I'll add one thing. When we're looking at the CPP, we may be purchasing, let's say we're purchasing CCIs and off-system RNG as our solution to meet the CPP. We still have to, we're still transporting that traditional natural gas to our customers through our distribution system. And then we're either retiring the CCIs or the offsets. And so that gas is still flowing that the distribution system, that the engineering team needs to plan for. Now there's consideration for on system. If we put an RNG project, let's say in Bend, which we have contracted for, we still have to look at it and analyze it and determine, is that RNG project reliable on peak day? If there's a cold event and that RNG project isn't able to produce as much RNG as we would on a normal day, that's something that we have to consider. But that's also something that we have to study and we have to analyze with our distribution system planning team. So just because there's the CPP, we still have gas flowing that we have to plan for on the distribution system side.
Yes, thank you.
Yep.
Okay, we'll move on. Now we get to get into projects, which is the part I like. But yeah, so these are our projects. I'm going to go over our projects for Oregon that are in our 5-year budget. Enhancements and reinforcements that are to address the deficits. So for Oregon, we have 4 projects I'll be covering. We've got the Prineville Gate upgrade, Baker City reinforcement and new gate station, Bend Shelburne Park reinforcement, and the Ontario reinforcement. So in this presentation, we're just going to cover capital budgeted projects over $1 million. For each project, we'll go over scope, cost, timing, benefits, and alternatives considered. So just with the IRP, I'll admit some of these projects have been covered in previous IRPs. Some of these are carryover from 2019 and 2021 IRPs. But that's just the point. There's continuous improvement, and we're saying these reinforcements are still needed on our system. As we do our assessments, we look at deficits. They've been looked at a couple times vetted. So first up, we'll start with the Prineville Gate upgrade. This is just a straightforward gate capacity upgrade. For this project, both the Cascade Gas Gate, CNG Gate, and TransCanada Gates will be rebuilt. I'm not gonna say price, they're on the slides, so cost is listed. For timing, we're looking at this one for 2023 design and 2024 construction. So go over a little more. So benefits of this gate upgrade, Cascade will be taking over regulation and will have the ability to bypass currently at this site, GTN has regulation. So we're very reliant on GTN if we need to bypass, if we see pressure drop or pressure droop out of the station, which is a little bit of an operations concern for us. Basically, what will happen is the current gate station will be replaced with larger size piping and facilities that will allow the gate to meet current demand needs and provide more reliable delivery pressures out of the gate to our transmission and high pressure systems that it feeds. With this gate currently, I think this was last year, but we've seen it had some gas control alarms where we've seen up to 30 pounds of droop out of the station, just kind of showing undersized components. For this one, alternatives considered, none. This one, basically just the existing gate needs additional capacity. DSM was not considered due to the urgent timing needs of the project. And then I also would like to comment on interruptible customers. Prineville has 2 RS-163 customers behind this gate. Interrupting these customers will not offset the gate upgrade. And then I just included a quick map on the Prineville gate. And then out of the gate, we have a couple miles of transmission and high pressure that go and feed down into the Prineville distribution system. Next up, I got the Baker City reinforcement and new gate station. So this is a new gate station on the east side of Baker City with a 1,200-foot 6-inch plastic reinforcement that'll tie into the distribution system. Currently in Baker City, it's served by a single gate and a single regulator station. So this project's going to provide a secondary reg and pressure source into the distribution system. Costs are listed. For this one, it was, and I think we're moving it in our budget, but we were planning on 2023 construction, but with discussions kind of with some of the 2021 IRP comments, we have proposed to push it to 2024 and 2025 due to DSM, as I covered previously. So good opportunity for this one because we have a little bit of time to see if we can reduce load. Benefits, the new gate station will provide a secondary redundant feed to Baker City. Will provide additional capacity, and it'll boost the design day pressures on the east side of Baker City. Alternatives considered for this one. So whenever you're considering adding a second gate, you always have the option of increasing, doing a gate upgrade on the existing gate station and then completing, you can always run larger size trunk lines or high pressure out of the gate deeper into the distribution system. That's always an alternative to adding a reg or a gate station. But this one, since you'd have to upgrade the existing gate station, it's kind of a wash. New gates or upgrading gates cost about the same than what we've seen. But the 1,200-foot reinforcement with this project is significantly less than what you'd have to do to upgrade the existing distribution system to get flows deeper north into Baker City. But the alternative we are considering, I guess, or we're going to try, is the targeted DSM. And then I'll show you a map. This one will make more sense. But this is the existing Baker Gate. There's just one rig that feeds the whole town, and everything in yellow is kind of an outline of our distribution system. Due to privacy, I have to kind of show limited information, and then this is the location of the new Baker Gate. So you can see it's going to put a new source up in North Baker City. That's the scope. Next, I'll cover the Bend Shelvin Park reinforcement. This is a high pressure main extension and new regulator station on the west side of Bend. This project consists of installing 1.8 miles of 6-inch steel high pressure pipe. Cost is listed. It was kind of planned for 2022, but it didn't get. It's not going to go forward this year, so it's going to be. It's currently scheduled to get completed in 2023. What we're hoping for. Benefits to this project. So I'll show you the map of Bend in just a sec. We don't have much high pressure or regulator stations on the west side of Bend, and the west side of Bend's seen a lot of growth with subdivision growth. So this will extend high pressure into the west side of Bend and put a reg station. So we'll have a fresh source to the distribution system. This project will also help eliminate the need of bypassing during cold weather events. The west side of Bend pressures have kind of struggled over the last couple years, and we've seen some pressure issues and alarms. This last February, the west side of Bend, where this reg station is going to go, dropped down to a half a pound when we had an average daily temperature of 13 degrees. Bend, just for reference, Bend design date temperatures is designed for minus 11 degrees. So we had almost, Bend potentially could have got 24 degrees colder, and I don't know if that half pound would have held. Probably would not have. So this new reg station is going to boost pressures on the west side of Bend, and it's also going to help support the growth we've seen over the last couple years. Alternatives for this one is, like I mentioned, so whenever you're considering a reg or extending high pressure, your other option is you could just reinforce the distribution system out of current reg stations. But that was, after going through alternative analysis, that was significantly more expensive, the amount of pipe and infrastructure you would need to install versus running a new reg station. And then DSM wasn't considered for this project due to the urgent timing needs, like I mentioned on that concerning low weather temperature. We had this in February. So here, I'll show you the map. So this is the Bend system. So Bend is served by two gates. This is the Bend gate and the South Bend gate. So both gates are on the east side of Bend. You can kind of see, so these red dots are existing reg stations. So you can kind of see an outline of our high pressure system and where our regs are, but you'll notice the west side of Bend is pretty scarce for regulators. So this project's going to extend some high pressure into West Bend and add a reg station to help the distribution system pressures. And then just a little background, I know I've provided this in other presentations, but the west side of Bend, this is kind of on the back side of Bachelor. There's lots of, the west side's kind of where a lot of the growth's happening due to the mountain, you know, lots of golf and mountain biking trails out here in Bend. So this is where a lot of the new homes are going in, being built into Mount Bachelor. Our next project, we got the Ontario reinforcement. This is this project's going to install a new reg station with 6,000 feet of 4-inch plastic. Here's the cost. Timing on this project, we were looking at this as a 2023 project, but we are going to push it and and do DSM on it, so it's going to get pushed in our capital budget to 2024 or 2025. So, and we'll cover Ontario in just a sec, but Ontario is similar to Baker City in that it's served by one reg station. So this is going to put a second reg station in Ontario. This one puts a reg station to the south. So benefits, we're going to get a new reg station and a 4-inch trunk line to help get pressures and flows into the south of Ontario. It will provide a secondary feed, so second source, a dual reg station. And then this reinforcement is going to kind of set up potentially, if they're needed, for smaller reinforcements to the south, because they're starting to see growth in Ontario on the south and east side. So it kind of sets up if, gives you opportunity for future alternatives considered. You know, with this, like I mentioned, so instead of adding a new station, you could always put larger size trunk lines from the existing station. But the amount of pipe you need to run out of the existing station is actually more significant than the 6,000 foot plastic reinforcement proposed. And then another thing you could always consider is you could run high pressure, but it wasn't considered due to cost. Here it's probably not quite big enough where you need a lateral. And then the other option which we're looking at and pursuing is the targeted DSM in Ontario. Now here's kind of the map of Ontario. So this is our current reg station that serves all of Ontario. And you can see this blue is a high pressure line. So we have existing high pressure, and this project's just going to drop a reg off our existing high pressure, and then we're going to build a trunk line out of it to get onto the distribution system. So puts a reg in the south. So yeah, that kind of concludes my distribution system projects. Yeah, Abe, I see you got a question.
Yeah, thanks, Kathleen, for this explanation. I understand that the reg station will cut pressure or regulate the pressure. So if is every reg station that you put in would require a trunk line to feed the distribution system from it? Because I understand that, or is it, can you just explain to me how that works? Because I know that when you operate, you need at certain points, you need to put some reg stations or something. So how does it work in relation also to the city gate?
Yeah, so outer rigs, you do normally have trunk lines. It all depends on the size. We go through velocity and like there's engineering sizing we do in our, good engineering practices. So we look at velocity and we size it, but it all depends on the town. So if you know the flow that needs to come out of your reg, that's all in Synergy. So we can dial up, put that length in, and look at those velocities and do good sizing. But a lot of times out of your normal distribution system regulator station, you might have a 4 or a 6-inch trunk line. And that'll go like the 6-inch might feed 4-inch trunk lines. And then those 4-inch will do 2-inch. So it's kind of like it's kind of like a stairs. So you work down. A lot of residential's 2-inch, but typically, 2-inch can only serve so much. You would have a very small station if, you only had 2-inch out of the station. So where that station ties into, it needs a trunk line because there's only 2-inch, and that 2-inch can't support the flows to get it out into the system. It can, yeah.
Oh,
Does that make sense kind of with the sizing?
Yeah,
So
it's
you
just,
normally need a trunk line.
Yeah, it's just because, when you said we boost the pressure by a regulating station, it kind of contradicts the concept of a regulating station. It doesn't actually add pressure. It's just it regulates the pressure from something that's higher pressure to a regulated pressure, I guess, or a lower pressure.
Well, it does. So if I was to scroll back to that example, where we had 10 pounds, that little example we worked through with the airport. If I dropped a brand new reg station down there, I'd have 60 pounds right out of the reg station. So the reg station is like an immediate source to your system.
Okay.
So it does cut. Yeah.
Yeah, it doesn't actually boost the pressure, but it's a new source to the system, I guess.
It will typically boost the pressure. Not like a compressor does, but yeah, it would. If I have a system that's currently 30 pounds and I put a new regulator station in, that regulator station, typically distribution is 60 pounds. So I would have a fresh 60-pound cut. So it would boost that 30 to 60.
Okay. All
right, that
makes
makes sense a little bit. Yeah.
Yeah.
Somebody else, I see someone else is flagged. Okay, I think hand popped up. Okay. So yeah, so this is kind of the last little section, and yeah, could be a little intimidating, but we'll get through it. But yeah, so iterative process and changing dynamics. So this is kind of some of the stuff we've been talking about. So with changing dynamics, there are a lot of potential changes coming to the energy industry, as we have discussed throughout this IRP. And I'll just list them. So we got renewable natural gas, hydrogen blending, building codes, electrification, demand side management, energy efficiency, and targeted load management. Some of these changing dynamics are relatively new, and some are becoming more and more established. We're, like we've mentioned, we're just getting RNG on Cascade, with recent contracts that have been signed. So as these changing dynamics evolve and are implemented on our systems, their impacts will be considered in our IRP process. And that's actually what I'm going to cover a little bit on the next slide. So changing dynamics, I thought it would be helpful to kind of help tie this presentation together to go over how these changing dynamics, will be and can be accounted for in distribution system planning. So I kind of divided them up and put them into buckets. And this is really high level because these are all kind of new and evolving, but I'll just cover each one and then give you a couple examples on what I mean by it. So both renewable natural gas and hydrogen blending, if those come on our system, like I talked about, they'd get added to our synergy models. As soon as they come on, they'd get updated. They'd also be in our rebuilds that happen every 3 years. So these would be sources, in synergy. They come right into play on our deficit assessment. So if a renewable natural gas project comes on in a an area with struggling pressure that maybe had a deficit identified and a reinforcement proposed, with our iterative process, that would maybe eliminate the need, or we might look into it and determine we no longer have a deficit. So that's just kind of how that would play in. And then with building codes and electrification, if this kind of has to do a little bit with growth, but if we're predicting homes are going to electrify, either existing homes coming off our system or maybe new homes just go fully electric, that would all be kind of in the growth predictions that are changing and reassessed on our IRP. It would also potentially be in building codes, because if they're predicting lower usage, or if things like gas furnaces aren't being installed in homes, it would go down on our growth prediction. So when we get those growth numbers, then we look at our systems and see if we have deficit. So that's kind of how it would be accounted for in the synergy models and in the growth predictions. And then with demand side management, energy efficiency, and targeted load management, that's kind of all accounted in our CC&B data. So every 3 years when we rebuild data, if we are seeing usage per customer declining, we think it might be a little bit of a lagging indicator, but it would be accounted for in our demands. So when those models get rebuilt, if we're seeing usage going down, that would all be reconsidered. So with all this, it'd be reconsidered on when we look at our deficits and then how to address the deficits. All this would kind of play in. And then, like I mentioned, we're annually reassessing, enhancement needs and deficits, and asking the questions, is this still needed, or can it be pushed out, or can it be eliminated? So we have kind of a constant feedback loop in distribution system modeling. And then just to further wrap this up, I wanted to kind of show our loop and our iterative process. So every 5 years, every 2 years on the IRP, we look out for 5 years. So projects that are identified in this IRP cycle, they're 3, 4, 5 years out, those will get reassessed in the 2025 IRP. So those will get relooked at. If those changing dynamics happen, they would, be reaccounted for. Maybe those deficits would be eliminated, and our capital budget would adjust as needed. So with this, with our IRP process, this 5-year process allows us enough time to plan, design, and construct projects to address deficits and be both proactive and reactive to the changing dynamics we have discussed. Overall, this whole thing gives me a lot of confidence that we'll be able to change and adapt to the changing dynamics in the natural gas industry. And yeah, that concludes my part of the presentation. I'll open it up to more questions. I know we've kind of covered them as we went, but yeah, I see Kim.
Thanks. Could you go back a couple of slides to the changing dynamics one?
Sure. This one or
that
the
guy
one
right there.
previous? Okay.
That one. So you said that you feel like this gives you, like, there's an opportunity here with the IRP and with the distribution system, I guess maybe modeling, to be both proactive and reactive. And I guess what I'm trying to see, like, when there's an interest in considering those non-pipe alternative solutions, where, like, is that, it seems like with this layout of sort of the different dynamics, that becomes more of a, I don't know how to say it. It's like sort of falling into the reactive side of things. And I guess what I'm wondering whether, which is to say, like, you look at trends in demand side management, or trends in energy efficiency, or trends in building codes and electrification, and incorporate that into the planning. But is there another way to be looking at these elements as helping to inform a proactive approach that, that is able to explore non-pipe alternatives earlier in that process. And maybe it is, I'm just sort of missing it, but like what I'm hearing makes it sound like it's more reactive than proactive, and that it's not clear sort of where a non-pipe alternative actually gets considered, other than anything as like sort of a sensitivity.
Yeah, so that non-pipe alternative is DSM, and yeah, it's considered an alternative analysis. So like Baker City, I think we are proactive on that one because we're choosing to do Baker City, which is the non-pipe alternative, to see if DSM can address the deficit.
Yeah, and I love it, and that's great. I guess I'm wondering, it's like whether maybe it's just a matter of, well, and you said it a little bit too, like that there has to be certain elements of the constraints that you're facing that lend themselves to those types of projects, right? Like, the urgency of it and sort of the, I don't know, just like what the elements are that make a project like that possible. I'd love to learn more about that, and like how can we better surface like where those opportunities are, and what are the factors that need to be sort of all aligned in order to make a demand side management project like that even a viable solution. Do you have is there more information on that and sort of what you're capturing for the Baker City project, and whether there are other things that we can be have heightened awareness about for other opportunities like that?
So the pilot program, that's kind of what we're going to learn, or what we're trying to get a handle on. But yeah, it's all new, and then really as the pilot program progresses, we'll have a lot more information in the next couple years. Hopefully definitely before our next RFP. So I think that's what we're trying to learn and gain, is get those programs online and monitor their effectiveness. But yeah, it's all kind of new, and this changing dynamic side, I'll admit it's intimidating. So
well, we'd love to just work with you closely on that and trying to understand sort of what those factors are, because it's it's new to us too, and we the more we can discuss it, I think the better.
yeah, right now for the non-pipe alternative with DSM, our main thing is we need enough time, and then it can't be an urgent need. Those are like the two that's like the main two things we're looking at on whether we consider it or not.
Yeah. Okay. Thanks.
Yeah. I'm gonna get off this slide. Any other questions? All right. Well, thanks everyone. I'm going to hand it over to the next presenter, but I appreciate your time, and yeah, staying involved in distribution system planning.
All right. Thanks, Kathleen. We'll take a quick 10-minute break. So we'll come back at 10:45 and we'll continue on with the presentation. All right, everyone, it is 10:45, so we'll get going again. We have a presentation from Ashton on Backcast overview.
Perfect. Thanks, Brian. I apologize right off the bat if I yawn or if I slur my words. I'm super tired. Daylight savings did a number on my 3-month-old, so that's been really fun. But I'll do my best here. So backcasting, I think technically we're supposed to be calling it cross-validation. Cross-validation is an estimate of the skill of a model on unseen data being data that wasn't used when you developed the model. So this can flag problems like overfitting, sampling bias, and a number of other errors that can happen when you're in the forecasting realm. There's a lot of different cross-validation techniques. A lot of them are quite complicated and out of the scope of what we're doing. But one of the popular ones you'll hear about, or I'm sure you've seen, is just simply called the holdout cross-validation method. This is where you take data, you split it into a training set and a test set. You develop your model on the training set, you then forecast and you compare that to the test set. And that's a really good way to see if your model can actually predict on data that's never seen before. And so if you remember back in Tag 2 is when I presented the entire demand forecast, and I promised I would do a cross-validation presentation. So that's what this is for. So it's kind of tying into Tag 2. I know that was a long time ago, but just bear with me. We can go to the next slide and I'll show kind of a visual. So here we have, this is kind of the format of what you're going to see in the next couple slides, but I just wanted to show what training set and test set look like. So for the training set, I took 2015 all the way to the end of 2021, and that's my training set. And I developed a model, and then I forecasted from January 2022 all the way out to, I think it was August is as far as I got for this year, and compared those to see how well it performed. And at the top, you'll also see a couple of other terms you probably hear in the industry, or maybe more in the statistics side of things, is you have an in-sample and an out-of-sample forecast. Those are kind of similar to the training and the test set. The in-sample forecast is essentially called in-sample because I started the forecast in 2015 using data from 2015 to 2021. So that in-sample part should be fairly accurate. I'm forecasting on data that was used to make the model. So it's kind of like this iterative, it should be accurate because that's the data that was used to train the model. So the bread and butter lies in that out of sample forecast part at the end. That's where the model's never seen that data before, and that's where you're going to see the accuracy and the prediction value. So if we go to the next slide, we can jump into some real-time results here. Oh, I'm sorry, I forgot about this slide. So I wanted to show just a quick last backcast we did for the last IRP was kind of the first time we had done it. I had only done some Washington city gates, so I don't have a previous cross-validation for Bend, which is what I'll show you in the next slide. But I wanted to show you, you have the black line, which is essentially just the real world billing data. And then you have the red line, which is our forecast. And you can see even in the in-sample forecast parts on the top left, which is residential, and the top right, which is commercial, you can see we're lagged behind the actual usage. And that's something we discovered doing the cross-validation the first time. Now, when you zoom out to the entire city gate and don't look at each individual rate class, you're not going to see this kind of detail. We didn't notice that there may be, we could get more accurate with our forecast. And so by doing this cross-validation, we noticed back in Tag 2, you'll remember, or you won't, that we figured out that customer billing cycles exist, meaning we dug into the data and noticed that sometimes a majority of usage might be getting billed in the next month when most of that usage was in a previous month. And that can really mess up some of your allocations and where the models think the demand's actually going to lie. So we dug into that and figured out which billing cycles needed to be shifted and which didn't. And you'll see in the next coming slides that this red line and this black line are going to line up a lot better. Also, you'll see it captures the valleys and the peaks a lot better as well. And then at the bottom, real quick, I want to make a comment. Just the bottom is industrial, Industrial is notoriously hard to forecast because oftentimes they don't respond to weather. They're not weather dependent. They have various different times during the year that they ramp up production, and it can be really tricky. But even the industrial forecasts were drastically improved by looking at billing cycles. So just wanted to throw that in there as well. So we can go to the next slide here. And this is residential. That's 101. This is Ben Loop. And you can see that the in-sample forecast part lines up really, really well. It's capturing a lot of those peaks. And then but again, the important part is after that 2022 vertical line, it's lining up really, really well with actual usage. It looks like we are slightly maybe under forecasting there, but it's very minimal. And so it's definitely something that I will keep an eye on to make sure I'm not consistently under forecasting, and maybe we need to look at why. But I'm super happy with these results, and I love the improvements that we've been able to make by doing cross-validation. And going to the next slide, it's a very similar story with commercial. So here you'll see very similar. It's capturing the peaks and the valleys really, really well. Again, very accurate on the out of sample forecast, but again, maybe we're slightly under forecasting that Ben Loop. We'll need more data, of course. It could line back up a lot better as we get further into the winter. Who knows? But it's something we'll want to keep an eye on. And yeah, so super happy with the commercial results. And then we can jump into industrial on the next slide. And this is a huge improvement from previous industrial forecasts. I know that the in-sample part looks a little messy, but it is a huge improvement, and industrial can be some of the most volatile and tricky ones to forecast. So you'll see I have a slide on next steps. One of the things I want to do is look more into regressors and other indicators that I could use strictly on industrial. Yeah, right here on this slide. So I want to look at things that I can do to help the industrial forecast be more accurate. And there might be regressors I don't even use in residential and commercial. So I want to be investigating that quite a bit as one of my next big projects. And then I also want to build a script so I can do faster cross-validation. This is why it's taken me from tag 2 to tag 5. I have other job responsibilities, but this is a pretty big project. It can usually take me about a week per city gate to do because I'm just kind of doing it all by hand. So I'd like to create a script in R so that and kind of automate that so I can speed that up and do a lot more cross-validation and do it faster and have maybe more results for you guys. But as it stands, I generally pick 1 to 3 city gates for each state, and I run through it. So that would be next on my list. I think that concludes the backcast portion of my presentation. I still have a couple more slides, but I wanted to pause if there's any questions on that. I see Abe has a question.
Yeah, thanks, Ashton, for demonstration. These are terms equivalent to HDDs, or if that's the full set of data? That's just HDDs, right?
No, this is demand in therms. This is the full demand profile.
In terms, full demand, yeah. So
yep, full demand.
Yeah, so you'd be focusing more on the peaks, right?
Yeah, mostly. Yeah,
that's the most important things, right?
Yeah, I would say peak day is very important. Yeah, and I also have some cross validation that I could do strictly on peak days. I just haven't done that quite yet.
So do you have a mathematical sort of function that will calculate how well those peaks are?
There's a couple.
How well the forecast matches.
Yeah, so there's a couple statistical measures you can use. I didn't want to bog down these slides too much with a bunch of error number values that maybe people didn't understand, but I think next time, since you're asking about it, I can throw those on there. There's a couple different commands in R that I can do. You can test the accuracy. There's an accuracy function. It'll give you a number. There's all kinds of root, mean square error. There's all sorts of different measurements we could use. So I think, yeah, next time, and maybe I'll even throw them in the IRP narrative. I can throw in some tables that show some of the improvements in those error terms. So you actually have like a numerical value that you can attach to rather than a visual.
Yeah, it would be good to focus on the peaks, of course, because that's the most important thing. But it's just some other means other than just visual.
Absolutely.
Yeah. Thank you.
Yeah, no, I hear you. Yeah, absolutely. All right, Brian, you want to go to the summary of alternative resources. So yeah, go ahead, next slide here. So we've already summarized these in a previous tag, but since we're going to be talking about portfolios, we wanted to quickly summarize what we're kind of talking about. These alternative resources are things that we give our modeling software the option to choose if it needs to meet demand or emissions restraints. So these could be things like incremental transport. So not excluding what we currently have, what more transport might we need? So this could be Northwest Pipeline, which would be that red pipe that goes from the top left Sumas down to Opal. It could be GTN, either direction, north or south. That's kind of that blue turquoise line, I think, from Kingsgate all the way down to Malin. Or it could be other smaller little transports or connectors like T-South or Pacific Connector. And so we want to allow Plexos as many options as it can, but we don't want to introduce any bias. So we just kind of allow all of these to be options. And we also do things like storage and stuff we'll get to. So the next slide we'll talk about, I think the next slide's storage. Yeah, so here we also allow any storage really, even stuff that we may not think as modelers are going to be selected. This could be like you'll see in California, there's Wild Goose or Gill Ranch. From our perspective, pretty sure that all the different pipelines we would have to put that gas on to get to our system, that all the different rates, you kind of create this rate pancake, it'd probably be too expensive. We don't want to introduce our own bias though, so we get the relevant pricing, we put it in, allow Plexos to choose if it's optimized that way. There's also storage around ACO, storage around Opal, all kinds of storage that we don't currently use, or maybe we don't think we may need, but again, we don't want to introduce our own bias. Next slide, please. Yeah, we'll talk about, and then of course, incremental supply. So this could be additional supply around the basins. This could be RNG, which would be directly distributed into our system. It could be hydrogen, again, directly supplied to our system. So these are all these options that we're allowing Plexos to choose from. If we don't give Plexos an option, it can't choose it. So we want to make sure we give this big buffet of options and then let it select what it thinks is optimized correctly. And then next slide, please. I think this is where we pass it off. Yeah, so I think I'm passing it to you, Brian, and you're going to talk about the components of what these portfolios that we'll be talking about, what those components might look like.
Yep, thanks, Ashton. Just to add on a little bit, that was the alternative options for upstream. There's also obviously alternative options downstream as well with energy efficiency, and we do model a higher DSM than expected. That's also included in these models. So just wanted to add that. So I'm going to jump into the components of candidate portfolios. And this is our supply resource optimization process flow. This is kind of the process that we follow when we are putting together our portfolios and running our portfolios through scenario and sensitivity modeling. You could see in this flow diagram where we input this data. So demand, supply, transport, pricing. We'll throw that into the as-is analysis, and we run a deterministic optimization of our existing resources. So any of our current resources that we use to serve our customers, that goes in our as-is. This gives us a very good detailed information of what our model currently looks like. And then we start to identify portfolios. We look at incremental DSM. So is there any way we can get more DSM? incremental transport. If we have a shortfall and we can't serve customers in an area on peak day, we may have to look at more transportation. Incremental RNG, incremental hydrogen. Is there more RNG and hydrogen out there than what is currently forecasted? So this is kind of the flow chart. I'm actually going to skip to the next slide, just because it's more of a step-by-step process, but we like to provide the flow chart so you can see how it flows. So like I had mentioned, step 1, we look at the as is, we look at our current system. Step 2, we identify portfolios. This is where we start looking at different portfolios. In previous IRPs, we would, for natural gas, our only option to serve customers was natural gas in previous IRPs. Now we're introducing some other supplies such as RNG and hydrogen. So our portfolios have changed quite a bit since the previous IRPs. Step 3, we analyze the portfolio. So each portfolio will be run through Plexos Optimizer under expected conditions. The portfolios will be evaluated under deterministic and stochastic weather pricing. In the stochastic weather pricing, we run 200 draws on Monte Carlo draws on weather, 200 Monte Carlo draws on pricing, and we run those through Plexos. The timing and quantity of unserved demand and emission reduction are recorded, and then we calculate a risk-adjusted total system cost of each portfolio. Once that's done, we go to step 4 and we rank the portfolios. So we take we look at them and we rank them based on, can we serve customers? Can we hit compliance targets? Those are our main goals. We want to make sure we hit our emission targets, and we want to make sure we are serving our customers. And then we'll take a look at costs. We rank them based on, can we serve them? Can we hit emission targets? What are the total system costs? So if you have multiple portfolios that meet compliance, serve customers, then we'll look at the cost of everything. So then we take that top ranked candidate portfolio to step 5, and we run it through 5 scenarios. These scenarios provide sensitivity testing of customer growth, energy efficiency, RNG, hydrogen, natural gas bans, and natural gas pricing. We also evaluate it under stochastic. So again, 200 draws of weather, 200 draws of pricing, and the timing quantity, if applicable, of unserved demand and emissions reductions are recorded. If under any of those scenarios or sensitivities we have concerns about that portfolio, we'll go back to step 4. We'll look at the next ranked portfolio and rerun that sensitivity and scenario modeling. Once we get through that, if we are satisfied with our, in step 6, if we are satisfied with the portfolio, we make that our preferred portfolio, and that's the plan that the company plans to execute and follow, at least for the next 2 to 4 years in the action plan. These are really important steps. If there's any questions, please feel free to ask. If there are any concerns or any ideas for how to tweak this in future IRPs, please let us know. We're always open to changes or analyzing things in a different manner, but this is the process that we're following for the current IRP. I'm going to leave it open for any questions for a second. All right. Well, go ahead, Abe.
Thanks, Brian. You said look back to step 5, and that's only one portfolio, which is the preferred one.
Well,
Would
it's
you ever,
only the,
would,
it's only the, so it's the top ranked portfolio. It meets, when we do our deterministic and our stochastic modeling,
Yeah.
it becomes our portfolio that serves customers, hits carbon emission reduction goals, and it's the least cost. And then it goes down. So we rank them. It doesn't become a preferred portfolio until we run through all of our scenario modeling.
which is step 5.
Yes. If we run it through step 5 and it comes out and we like the results, it meets compliance, we don't have any concerns, then it becomes our preferred portfolio.
So what do you do in step 6? Wouldn't you go back to, if step 6 has got some risks attached to it, wouldn't you go back to step 4, or you would still, what would you do in step 5 different if step 6 is not satisfactory?
So yeah, we would go back to step 4 and we would grab a different portfolio, which could be an RNG only portfolio, or RNG and hydrogen only, and we kick out offsets or something. That would, then we would move on to step 5 and we would run the
Yep.
scenario modeling on that portfolio.
Thank you.
Yep. So just to give a reminder, the recap of the as is, we made some assumptions. We assumed that contracts would evergreen. If we didn't, we would have contracts expiring. So upstream transportation contracts would expire and we would not be able to serve customers. We assumed emission reduction requirements as outlined in the CPP and CCA, but no usage of compliance instruments. These preliminary results do not include the impacts of incremental DSM beyond existing installed measures. So that's something to keep in mind when we discuss as is throughout this presentation. So when we look at just the as is, we have some shortfalls. We would be unable to serve customers on transportation in zone 11, which is up here in the Yakima area up to Wenatchee, starting in 2034, and then zone me Washington. So the GTN is this blue line that comes down, and in this area in Washington and Central Oregon, we'd run into shortfalls. And if you recall from tag, I want to say tag 4, it may have been tag 3, when we did include DSM in this analysis, we just plugged in DSM only, and it was able to push back these shortfalls. So the zone 11 went back 12 years to 2046. That's when we saw the first shortfall. And then in zone me, Washington and GTN, there was it pushed it back to 2049. So it pushed it back 11 years. So DSM does have a big impact on transportation. Obviously, if we didn't have any compliance instruments, if we just kept business as usual, well, we would not be able to meet carbon emissions. So it's definitely CPP in Oregon, CCA in Washington. Those are definitely top of mind when we're analyzing our portfolios. The list of candidate portfolios. We have our all-in portfolio. We do an all-in portfolio without any DSM, any future DSM. Transportation only portfolio. So we just look at adding transportation, offsets only, RNG only, hydrogen only, and then RNG and hydrogen only portfolios. And we'll jump into each of those. So if you have any questions, we'll go through them real quick. That way you can see what's all included. So the all-in
Okay,
portfolio. Oh yeah, go ahead.
I do have one question. I thought earlier in the presentation you mentioned the sensitivity to growth, and I don't see any of these portfolios that indicate how you're handling that. I would have expected you to have a high growth, medium growth, and low growth or something portfolios.
Yeah, so we actually run high growth under the sensitivity analysis. So these portfolios, these are ways that we are going to serve our customers and meet carbon emission targets. When we do sensitivity modeling, I think there's a slide, it's a little further down. We talk about high customer growth, which I believe is scenario 5, and we'll show the impacts.
I apologize. I only got partway through looking through your presentation.
No problem. We have a scenario of high customer growth, and then we have a low, but we call it electrification scenario. So it's basically if we see electrification in Washington and Oregon, we'll show the impacts that has on our modeling in our portfolios.
But are you saying that they don't affect the portfolios? I mean, I'm kind of surprised to hear that they're treated totally separately, that it's going to be a lot easier to make compliance if you don't have as much growth or if you have more electrification.
Right. So the portfolios, the way that you can think of it is it's all the resources that would be used to serve customers. And then we take those portfolios and we analyze them with different customer counts.
Oh, okay. All right, I'll wait until.
Yeah. So once
keep any more questions until you get to the end.
Yeah, exactly. Yep. Okay, so all in portfolio. This is the best deterministic mix of all alternative resources considered. So incremental transport resources, incremental storage resources, cost-effective DSM from the CPA, incremental RNG, incremental hydrogen, and then compliance instruments. So what happens when we plug all these in, we run our model, and we say, make sure you serve customers, make sure you hit carbon emission targets, and then give us the cheapest, the lowest cost route to do that. And so to meet the CPP compliance, we have a incremental RNG, all cost-effective DSM first. So you could see here we have the blue line. This is our forecast, assuming only historical energy efficiency appliances go in, and this would be our demand forecast. Then we plug in future DSM. So if there's any future appliances that go in that would reduce emissions or reduce usage, that's the orange line. So this is what we're planning for, is demand less DSM. So we're allowed no cost allowances through the CPP, and those decline over time down to, I think we're allowed 10% by 2050. And so that is the anything above and beyond the red line, we have to meet with no emissions. So anything that doesn't have an emission tied to it. In the early years, a lot of Oregon CCIs, and then beginning in 2024, 2025 timeframe, we'll be including RNG. This is a combination of on-system RNG, like bin landfill, and other on-system projects, as well as environmental attributes. And then beginning towards 2030, the end of the 2020s, green hydrogen is looking like it would be a cost-effective option for us. So we have green hydrogen in there. It is limited to, in our base modeling or all in, it's limited to 20% blend. So we can only blend up to 20% of our traditional gas. And so that is, even though it's cost effective, it is limited. So here on the left, incremental RNG utilized mostly in Oregon, 154,000 decatherms starting in 2023, up to 15 million by 2050. Hydrogen beginning in 2029, 90,000 up to 500,000 decatherms by 2050. And then compliance instruments will utilize those as needed. The exact number will be discussed under confidential treatment in the IRP. Kim, I see you have a question.
Thanks. So this is something that I'm like trying to wrap my head around. I think I've been trying to wrap my head around it in the Northwest Natural IRP, and maybe it comes up here too. But are you seeing well, the cost-effective RNG, both bio and hydrogen and synthetic, I suppose, influencing what is considered your cost-effective DSM, and like how are you sort of how are those two variables interacting with each other? I feel like it was a little bit of a novel process that I'm seeing in Northwest Natural in terms of like, you know, they affect each other, and when you plug it into the model sort of matters, and there's some adjustments that happen. Can you, and I'm sorry, that's not very specific. It's partly because I still don't really understand it. So if you can add any more color to that, that would be really helpful.
I can jump in if you want, Brian.
Yeah, go ahead.
So I think this is a great question. When it comes to trying to figure out how those two are going to ultimately interplay with each other, we're still learning about that. But I think one thing that we did try to do for this IRP process was in our avoided cost calculation. You'll notice when I start talking about the scenarios that we run, one thing that we do in scenario modeling is adjust the commodity cost portion of the avoided cost, because that's really what the RNG side of it is ultimately going to change, right? Is it's going to be, that's a much higher commodity cost. So in our scenario modeling, when we talk about our base case CPA inputs, that's going to just be traditional commodity cost, the way that all utilities have done it over the past using our price forecast. But when we start talking about increased DSM potentials, that is a scenario, a sensitivity toggle that changes that commodity cost to a weighted blend of those green gas resources, right? So it's a weighted blend for us of it's just RNG and green hydrogen, depending on how they're utilized in a given year. That portion of the avoided cost is increased based on that, using that resource, and then the result of that is a higher cost-effective DSM that's kind of thrown in before it even selects RNG, which it creates that potential iterative loop process where you could theoretically keep doing it. We don't, right? We just kind of say, okay, we're going to use what deterministically we would have selected for RNG or hydrogen. Let that be the blend that dictates what the commodity portion of it is, and then run this new DSM or this new CPA, get the higher DSM potential, kind of just put it in there once, and then see how that ultimately changes the need for other resources. So, you know, how does that decrease the need of RNG? So it's not, you know, if you were to try to make it an iterative process, you would get stuck in that forever iterative loop. But we do kind of a one-off adjustment analysis on that for those scenarios where we look at that higher CPA.
Awesome. Thank you so much, Devin.
You're welcome.
Thanks, Devin. Abe, do you have a question?
Yes. Thanks, Brian. I was expecting to see the hydrogen portion increase because your axis, your vertical axis is actually actual emissions, not percentage. So I understand that the RNG, is that because the RNG is not considered part of the natural gas system, so it's 20% of the gray area? But you're limited to 20%, right? So is it the gray area it doesn't look like it. So I was expecting the hydrogen to be more variable than this, than being a constant amount. Hydrogen displacement, I mean, of, yeah.
Yeah, that's a good question. I'll have to go back and look at that.
That's just from a sort of conceptual point of view, you know, like it just struck me that, yeah, it is constant, but it's constant as percentage-wise, unless you're looking at only the natural gas portion of it.
I can weigh in on this. So
Yeah.
it may be one of those that it's increasing at an amount that's not visually derivable. But yeah, we can definitely go back and look and confirm. But my inclination is that I would agree with you. It should be, because it's 7% of the gas supply itself is what we constrain it at. And that supply, it should be going up as we're increasing demand.
Yes, but only the demand that is not renewable. It's not
Correct.
RNG.
Yeah. So, well, so
So that's why there is a counter effect of RNG here. So it might be actually reducing even. I mean, it might be less even. I don't know, because you won't be counting it if it's displacing RNG, really.
Right. Yeah. So if it's displacing RNG, you won't be. Yeah, and that's one of those things that's super tricky because it ends up being a moving target in that modeling because of that exact effect that you're talking about. Yeah, we'll have to go back and look at exactly what the impact of it is, but I'm pretty sure that the way we modeled it. Well, so okay, I'll throw a caveat in. I'm pretty sure that the way we modeled it is 7% of the overall gas supply, right? So that includes traditional gas. It also includes RNG, but it doesn't include CCIs taken, obviously, because that's not a gas. The tricky part, and Brian's talked about this in some of the past tag meetings that we've had, is Plexos is not really that good at doing moving targets. It doesn't allow you to set a constraint to be variable. The constraint has to be fixed. So I think we do allow for some of that increase, but it's not going to be as 100% precise as we would like it to be. But we'll go back and check, and I think that green may go up at just a very small rate. But we'll go back and check and talk about that in the actual IRP document itself for sure.
Okay, thanks. And just the other follow-up questions is that with the renewables and electricity being more surplus eventually than demand, are you taking the conservative approach that maybe we will not be, it would be very, well, theoretically it would be very cheap to actually produce hydrogen. Are you taking the conservative approach that we will not exceed the 20% blend? That's a question for Brian.
So we do model a scenario where we have 30% blend, but as of right now, we would have to do our own. I know there's a lot of studies out there right now on hydrogen. We would have to do a study on our own system to see how hydrogen reacts on our system. Right now, it's our understanding that 20% is safe, but we would obviously that number it's something that we're going to be monitoring quite a bit. And if it's determined that 30% is the safe number, we would definitely go into our modeling and update it. But as of right now, our understanding is 20% is the correct number to go with. I don't know if anyone else has anything to add to that.
Yeah, it's Kathleen. I'm on the GTI committee, and there's a lot of variables. It might be system by system, or some of this, leak detection. There's a lot of things to kind of figure out with that hydrogen. I'm sure everyone is aware of. But yeah, might be replacing components or different things because those smaller molecules, could have more propensity for leaks. So.
Just my question is just being open to even new industrial customers having hydrogen pipes, piping separate, 100% hydrogen, things like that. That is going, the research is going on, and I think there are pilot projects already for these things. So just wondered if the scope or the Texas will allow you to do that. Probably there's no reason it will not allow you, but just the thinking that hydrogen can have quite good potential, especially with the abundance of renewables that are expected, especially during the day. I'm probably a little bit biased because I come from Australia, and that's already happening there, and the serious work on hydrogen because of that. The penetration of renewables has just gone a bit wild. Thank you.
Yeah, and one thing also, and this is still pretty early on, so it's not enough for us to make it a serious consideration in the quantitative aspect of it, but qualitatively, we are absolutely looking at kind of independent hydrogen systems, so 100% H2 delivery towards some of our maybe larger industrial customers, perhaps. There's kind of dedicated systems. Don't have anything substantive to report on that yet, but it is absolutely a consideration for us.
Yeah, and if it happened that we got industrial customers that were using only hydrogen, we would be able to put that into Plexos and be able to model that.
Thanks.
Yeah, thank you. Great questions. So here's the total system cost, the baseline total system cost. This is just our pipeline and storage information, and then any costs that are tied to emission reductions, so RNG, hydrogen, allowances, CCIs, anything that would be tied to those, that is put in the green piece. And then these are stacked on top of each other. So you could see total system cost as we increased our emission reductions. You can see that the total system cost increases over time. Yeah, go ahead, Abe.
Sorry, that was an old hand. Forgot to remove it. Thank you.
No problem. So you can see total system costs increase about $250 million starting in 2023 up to about $800 million in 2050. And we don't have customer bill impacts at this moment. That is something that we're currently working through, and we will be providing in the IRP narrative. It'll definitely be there for the draft and in the final. So the all-in less DSM portfolio, it's the same exact thing as before, but this time we don't include any future DSM. Just to see what the impact is. As you can see, we'll need more RNG, we would need more CCIs, we would need more hydrogen to be able to meet demand. Those costs would increase the portfolio, as you can see in this next slide, it actually exceeds 800 million and it touches the 900 million $1,000 and by 2050. So you can see demand side management, energy efficiency, it has a very big impact over time, very big cumulative impact. Incremental transportation only portfolio. So this is where we just increase our transportation to serve our customers. We also include the cost-effective DSM. As you can see, we would not be able to hit carbon emission reductions if we do not purchase CCIs or RNG or hydrogen. So this portfolio basically gets thrown out immediately, just because we would not be hitting CPP targets. Costs are very low, but that's because we have unserved demand. We would definitely need to look at penalty costs, which I think we included on the next slide. Here's emission costs due to penalties, and you can see that that number is huge. So we'll definitely be hitting the CPP targets.
That's good to hear. Hey,
Yeah.
thank you, Brian. Hey, one thing to note, I just, in terms of, and you know, it's just worth noting that generally speaking, we're going back through and we're looking at precedent around penalties, and unless there's an extenuating circumstance, penalties don't flow through rate payers. So I don't know how that, you know, we'll have to think through maybe as a group collectively how that risk is reflected. But it shouldn't, you know, it's more of a conversation for IRPs than it is like a mandate from us right now. But it is a risk that we want you guys to consider. But I think the precedent is such that we would, in the past, penalties have not flown through to ratepayers when they've been avoidable. We've insisted they go to shareholders. So,
gotcha. Okay. Thank you for that, JP.
But thanks for breaking that out and assuring us you'll be compliant.
Yeah. Offsets only portfolio. This is where we just look at community climate investments and auction allowances and offsets in Washington. As you can see, we'd be able to meet CPP for a little bit, up until about 2026, a little bit of shortfall here in 2024. But after that, CCIs, they do decline. The amount of emission reductions you need increase, so we would not be able to meet CPP targets with that. So we throw this one out as well. You can see total system cost. If you're interested on the impact of just the CCIs and the allowances in Washington, here's a good graph that shows the total system cost just based on offsets. RNG only portfolio, this is where we consider only RNG. We do see that we could meet the climate protection program in Oregon with just RNG. There's RNG is plentiful that we're seeing based on the analysis and studies that we've seen forecasts for. We would not be able to meet shortfalls in Washington based on the current rules because they do not allow, as of right now, they don't allow off system, but that's being reconsidered. Yeah, JP, you have a question?
Yeah, thanks, Brian. Sorry to interrupt. Just in terms of the IRP, are you going to make that study available that shows the availability of RNG?
Yeah,
okay.
Yeah, we'll make sure that our hydrogen, the supply and RNG supply, the projections, we'll make sure we source that information where we're getting it from in the IRP.
Yeah.
And then as well as the pricing information we're getting.
You know, and
that
in,
would-
in
Yeah, go
terms of the, Brian, and we don't have to high center on this right now, but you know, RNG flows across. I know you guys know this, a lot of different markets, right? It's not just the natural gas utilities competing for this. So any analysis would be great to incorporate that in, because we're thinking right now with another IRP that's going in, so we're looking at the transportation markets and what's the value of that fuel in those markets, right? And as it becomes available, you know, things flow to where the money is.
Yeah.
All right. Cool. Thanks.
Yeah, thank you. Yeah, Kim?
Thanks, and I would just add to that. I don't know. I don't know whether this is possible, but if recognizing that closer to home, you're going to be competing for that RNG with the other LDCs in Oregon, and making sure that projections attempt to sort of look at the amounts that other companies are trying to procure, and I don't know, just reconcile a little bit that, but knowing that even just locally there's going to be competition for that RNG.
Yeah, definitely.
This is Devin. So just kind of want to chime in. One thing, just as a reminder to all stakeholders, I think we spent quite a bit of time talking about what our methodology was for kind of what we would consider our, I know I always say this, but I hate this term, but our share of RNG that we would be entitled to, because we wouldn't be entitled to it, but essentially what would be our share of RNG, right? So it was a kind of pretty in-depth analysis that looked at the national picture, looked at how our load compared to other both regional and nationwide gas usage using EIA studies on usage. So, you know, I do think we did a pretty robust analysis of not just saying, oh yeah, we're going to be able to get all the RNG we want, but kind of trying to weigh these forces of there are going to be a lot of competing parties for it, but we are also going to be a lot more competitive than, say, a utility in, I'm just going to pick on Kansas, but Kansas, which I don't know their policies, but presumably they may not have as much competitiveness for those resources, while our local markets, such as, you know, Washington, Oregon, definitely going to be more competitive. So we try to account for all of those factors when figuring out what our share, once again, for lack of a better term, of RNG would be. And we'll go over all of our calculations. We did talk about them in prior tags, but of course, you know, we welcome feedback in the draft. It may be too late to make any adjustments to what our methodology would be for this IRP, but we're more than happy to revisit that methodology. And we're obviously going to get better at it as well as we're continuing to be a player in these markets and seeing ultimately what we're able to get.
All right, thanks, Devin.
Hey, Devin, just a quick response. Thanks for a reminder. I forgot about that. I'll have to go back and look at it. That's a great reminder. You guys did do that. I forget off the top of my head. I think one thing we're becoming very aware of is, like, you know, what RIN is value, you know, the value of a RIN in the federal market, the value of RNG and the low carbon fuel standards across the West Coast. So just, it's something that's becoming more salient to us now with the CPP and the IRPs in front of us. So just when you send that the tag that it was in, just so you know, this is kind of what we're thinking about. Just the overall demand, like Kim was saying, the overall demand.
Absolutely, for sure.
All right, thank you. So here's the total system cost for the RNG only. You can see it goes up to a little above 400 million, but we're not considering this one just because it doesn't hit the emissions reductions in Washington. Hydrogen only, cost-effective DSM and hydrogen. You could see because of blending issues, we would not be able to meet. My guess is I don't know if there would be enough if we could blend even higher, if there'd be enough. We'd have to double check that, but as of right now, just the current blending that we have understanding of, we would not be able to meet it with just hydrogen. So again, it's not considered. Here are the hydrogen costs if anyone is interested. Just looking at what the hydrogen only total system costs are. And then we do also run renewable only portfolio. As you can see, again, we would not be considering this as it doesn't meet reduction shortfalls in Washington. And we look at the IRPs as total system modeling. One thing about these portfolios is even though they don't meet reduction shortfalls, you can look at these and you'll notice that hydrogen is being taken over continuing with RNG. So you may be able to make that assumption that hydrogen is cheaper than RNG here. So if you want to just look at RNG versus hydrogen, you can also look at these portfolios. Taking a look at the total system cost, we get to about $400 million by 2050. So the methodology behind ranking the portfolios we discussed a little bit earlier. We use deterministic results to identify the intrinsic value of portfolio and the value of risk analysis to capture the extrinsic value. We rank these primarily on their peak day unserved, as well as meeting carbon compliance targets, and then by their total system cost. Results are given, deterministic results are given 75% weight, and the stochastic results are 25% weight. This gives us the Cascade risk-adjusted results, and the 75-25 breakout, this is kind of industry standard. We've been using it for 1 or 2 IRPs now. But these lead into the costs that you see on this next slide. Portfolio 1 meets, as you recall, it meets the carbon emissions. Portfolio 2 meets carbon emissions. 3 through 7 do not meet it in one of the states or the other. So we kicked those out already, even though the costs are below this. So between Portfolio 1 and Portfolio 2, because of that incremental DSM, or the DSM, the future DSM that we expect to see, it makes things cheaper. And so we will be moving forward with the preferred portfolio, or not the preferred portfolio, the top ranking portfolio with the all-in with DSM. You can see emission reduction shortfalls. No, we need emission reductions. It's the cheapest option. So that's the one that we will be moving forward with. And just to recap what that was, cost-effective DSM, it's the all-in with DSM, cost-effective DSM, incremental RNG, incremental hydrogen, and then obviously compliance instruments as needed. Are there any questions about the portfolio modeling and coming up with the top ranked portfolio? I'm going to talk a little bit about stochastic model methodology. So this is where we utilize Monte Carlo. So we basically create multiple different weather patterns, price patterns, and we can run our Plexos model on all these different weather and price patterns, and it'll give us different outcomes. So just a little bit of a historical look. We used to use SendOut, and it used to have a function within SendOut that would run stochastic analysis for us. It did have computational limits to the number of draws and the time it takes to complete those draws. So what we did is we pulled Monte Carlo simulations out of SendOut, and we would run them in R. It's a free statistical software if anyone is not familiar with it. And we would run our own simulations. In 2020, we enhanced it by by including correlation between basins. So ACO and Sumas and Rockies, there is some correlation between the pricing there. If pricing goes up in one area, pricing usually goes up in the other area. And so when we create our Monte Carlo for pricing timeframes, we want to make sure that we are keeping it realistic. Similar for weather, if weather goes up in Pendleton, it's probably going up in Central Oregon and Baker City as well. So there's some correlation between weather locations that we want to make sure we capture. That way we have realistic weather and price patterns that we plug into Plexos. So what we've done is we performed 10,000 draws. Now, there are some computational limits still within Plexos because running one of the models, just running one 28-year model, Plexos model, it takes probably about 40 minutes. So if you run 10,000 of those, you're looking at 400,000 minutes. So we have to limit the number of draws that we actually run. We do like to run 10,000 different draws. That way we can get a wide variety of price patterns and weather patterns. But we only are able to plug in 200. So for weather, we record the daily mean temperature, standard deviations, correlations, and the largest one-day jump to have historically occurred. We utilize those to create our different price patterns. For each basin pricing, Cascade records historic averages, lows, highs, standard deviation, and correlations. And then all this data is loaded into R, where R can perform 10,000 unique weather patterns and price paths. In R, performing this part in R is very quick. I mean, relatively compared to Plexos. We can do 10,000 draws within a day or so. So that part's the not so difficult part. It's plugging it into Plexos and running that optimization. That's the part that takes up some time. So to continue on with the weather, we run the first draw, and then the remaining draws are then correlated to that. So we go down for, so let's say Bellingham, we run Bellingham and we just do full Monte Carlo simulation on it, give us random numbers, make sure it's somewhat correlated from day to day. We don't want to see a 5 HED day one day and then the next day see a 75 HED day. They have to be somewhat correlated. Temperature doesn't just jump from day to day. And then we make sure to use Koleski decomposition to make sure that they are correlated between between weather locations. It's repeated 10,000 times. That's how we get our 10,000 draws. And then similar process is followed for price, where Koleski decomposition, we correlate it between the basins. So here's our historically correlated weather. You can see if you want to look at how is Bellingham correlated to Bremerton. They're pretty close to each other, so you would expect them to be more correlated. If weather is cold in one area, it's probably going to be cold in the other area. So you can see that those are pretty highly correlated. Areas that are further apart, Bellingham, let's say Bellingham and Baker City, those are really far apart. They have different climate, but they still are somewhat correlated, right? During winter, it's going to be colder. During summer, it's going to be hotter. You can see with using Koleski decomposition, we get some pretty accurate correlations between weather locations. if you just ran Baker City and said, do your own thing, Bellingham, do your own thing, Bremerton, do your own thing, there's no correlation between them. So we want to make sure that they're somewhat correlated. So we use this Kolesky decomposition matrix. If anyone's interested in how that works, feel free to reach out to me. I can walk you through it. In previous IRPs, what we would do is, because send-out would take so long to run one model, so like I discussed, Plexos, a model takes 40 minutes. Send-out with that same model, it took 4 hours. So previously, in previous IRPs, it was just too difficult to plug in multiple draws and run send-out. So what we would do is we would find 99th percentile weather, 99th percentile price, and we would plug that in and see what the impact would be. Now what we're trying to do is we're going to plug in 200 draws back in to Plexos, just because it's a little more reasonable to run those in a timely manner. 200 draws still takes a couple days to run, but before it took a couple weeks. So that's what we'll be doing for this IRP. And you can see here, Monte Carlo, this is just on weather. So we run just our weather. And you can see that demand varies quite a bit, over 1 million decatherms just in Oregon. And this is on the Oregon core demand. So you can see the impact weather can have. And I actually wonder if it's in my notes. I want to say this, that I looked at, I believe it might be on this next slide. Yes. So here on this next slide, this is the second compliance period that I want to take a look at and just show the variance that weather can have on demand. And so this is 2020, oh man, 2026. Well, the first compliance period is 2022, 3, and 4. So this is 25, 26, and 27. You can see that it goes from about 46 million decatherms for that 3 years to 47 million, which this is a variance of about 16,000 metric tons of CO2e just from weather variance. So that's something that we have to keep in mind when we're looking at meeting carbon compliance. Just weather could make it so we have to account for 16,000 more metric tons of. It also could go the other direction. If we have a compliance period on the low end, we may not have to buy as many CCIs or something. So that's something that is very important to our analysis, and we want to make sure that we have an understanding of the variance that we are looking at with carbon compliance. So total system cost. How does total system cost vary from the Monte Carlo simulations? And you can see on a low end, we're looking at $12.6 billion over the 28 years to about $12.7 billion. So you can see that there's, just based on weather, there's about $100 million of variance that could be caused. So these are just important things that we need to know for our modeling, for looking out in the future. So taking a look at pricing results, you could see 10,000 simulations of ACO. When we look at all 10,000, you could see that there are some draws, and who knows what may happen. There's a 1 in 10,000 chance that, and this is on traditional supply, just to clarify. there's a 1 in 10,000 chance that prices go up to $100 per decatherm. When we look at the 99th percentile, and we want to take out that upper 1% of things that could happen, the black swan events, we're looking at more reasonable natural gas falling under $25 range per ACO. We show this for all the basins that we purchase traditional gas. So Rockies, again, 10,000 simulations could get up to $50. The more 99% confidence that it'll stay under $20. But these help give us a different price patterns that we can plug in. If we plug in, let's say, one of these higher draws, does it start looking at more RNG instead of traditional gas, hydrogen instead of traditional gas? So those are important things to consider. Here we have Sumis. Sumis is a little more volatile. You can see in this 10,000 simulations, it gets pretty high. And then when we look at the 99th percentile, it falls under the $50 range. Are there any questions on stochastic modeling? We'll have more results and more narrative on the results in the IRP draft when that is filed. But are there any questions in the meantime?
Hey, Brian, this is JP. Hey, do you have any stochastics kind of going in the direction of demand falling? Like, so I'm just, if there are local ordinances, against new hookups, that type of thing that impact demand, maybe it's not as I should put it, it's not as robust a set as like Sumis price simulations, but do you have something like that where you can stress test portfolios going the other direction? With the growth, like negative growth?
Yeah, so it sounds like you're talking more about like Monte Carlo simulation on like customer counts.
Sure, yeah, that you made me sound more articulate. That would be great.
As of right now, we don't. We look at the customer counts as more of the high customer count and then the low customer count, but it is something that we'll definitely want to consider, just because customer count does have a big impact on usage, obviously, and knowing the different customer patterns that could be out there. Yeah, I think that's definitely something that we'll need to look into, and we haven't done it yet, so I don't know if it's something we can squeeze into this IRP, but it's something that we definitely want to consider. We do feel like we do have it covered with our high customer scenario and our electrification scenario. Those are kind of extreme cases, so we do think that we covered the extreme basins, but I think we could consider Monte Carlo simulations in future IRPs on customer counts.
Okay, thanks.
Are there any other questions? Okay, we have probably about 45 minutes to an hour left. So I'm gonna pose a question. Do people want to power through lunch, take a quick 5-minute break, power through lunch, finish this out, or would people rather take an hour break, eat lunch, and then come back? Anyone?
Either way works. I can power through if you guys want to do that and take a 5-minute.
Okay, my recommendation is 5-minute break, power through. If anyone does not want to do that, please speak up. Yeah, I'm not hearing anything, so. Okay, well, let's see if
I always like the lunch, but I don't think I'm the majority. Maybe half hour lunch? I'm not presenting though, so I think it'd be like maybe the presenters, like if they're how their blood sugar levels doing. I think they
yeah,
can make it.
Yeah, Devin, how's your blood sugar?
Don't worry, I didn't pass out. No, I'm ready to go. I think 10-minute from Sebastian is a good call, and we can
Okay.
get the party started.
All right, let's reconvene at 12:10 and we'll finish this out.
Is anybody there?
I'm here, Kathy. What's up?
Yeah.
Our leasing office forgot to tell us that we were going to have a potential complete outage of our internet. And so I'm finally back on using my personal hotspot on my cell phone. So are we on lunch break?
Just a short 10-minute, probably about 7-minute break now. And then we'll be picking up. We're gonna try to power through lunch.
I beg pardon?
We're gonna try to power through lunch. Yeah.
Okay, great. This is the part I was interested in. So
awesome.
Isn't communication fun?
Always something.
Yep. Oh, this is Devin. Hi, Devin.
Hello.
The fun is going to be when I go to try to connect everything, because I ended up unplugging my router in order to keep it from switching over to the system.
Oh no.
You still there, Devin? Oh, boy.
Devin, are you back?
I most certainly am.
Okay. We will go ahead and get going again. You're ready.
Absolutely. Okay. So let's spend some time talking about some of the scenarios and sensitivities that we've modeled. So Brian already kind of alluded to this in some of our earlier conversations about kind of the portfolios and then the scenarios and sensitivities. And this is also kind of, we talked a little bit about this in the flow chart that Brian showed, where we had like the steps. This is the latter half of the steps, right? So at this point in our process, we will have identified a portfolio that is that top ranking candidate portfolio, that under those expected conditions, deterministic and stochastic expected, which is kind of like a misnomer, but those expected conditions, we've identified that this portfolio seems to be the best fit for us, but we want to check it. We want to make sure that in certain extreme situations, it still ends up holding up as a solid portfolio. And if not, we want to be able to identify what are some of the potential flaws with this portfolio. And then once again, as Brian said, if it ends up being a flaw that's identified in scenario modeling that's too extreme of a problem, we have the option to reject it and move on to another portfolio. So different from this IRP, in the past, we kind of took a little bit of a scattershot approach, and we got some really good feedback that it's good that we evaluated a lot of different things, but it kind of took away from our ability to really do an in-depth analysis on the things that we were modeling. So we would do something like 28 scenarios and sensitivities, and we would just kind of present the results, right? So we'd put a table in the IRP and say, here's what the dollar impacts, kind of, we'd show some of the quantitative impacts, but we really didn't talk about what that meant. And that feedback we got was, hey, if for people to get an actionable feeling of what to take away from this, they're going to need that kind of analysis from you guys as to what should they be taking away from these scenarios. So that's what we've done. We've scaled back to a much more compact number of 5 scenarios plus our base case analysis. But in each of those scenarios, we're really going to include a robust quantitative and qualitative analysis of what some of the changes are to cost, what some of the changes to bill impacts are. That's a big thing, especially in Oregon. Part of the UM 2178 results that Oregon staff came back with is they really wanted to see bill impacts in the IRPs. And so that's something we're actively working on right now. We have some preliminary results, but nothing that we're ready to share yet, but we will be including that in the draft IRP. So bill impacts, costs, our abilities to meet our emissions reduction requirements and still do that least cost, least risk planning. Before we move on, I do want to do a bit of a kind of verbiage clarification. This has come up in a lot of past IRPs, is what is meant by a scenario versus a sensitivity. We've actually changed our usage of these words. A scenario for our purpose is going to be kind of a series of assumptions, and those assumptions are the sensitivities that differ from our base case modeling. So we have those 5 scenarios, and each scenario is comprised of a number of sensitivities. And so sensitivity you can think of as a variable within that scenario that we can choose to modify, that may or may not be modified based on the overall philosophy or kind of purpose of the scenario. That'll help us reflect the assumptions of that scenario. So just as an easy example, for instance, we have a high growth scenario, right? And one of the sensitivities that would be in that would be our growth. It would be we would use a high growth forecast as the sensitivity for that. We also may use a higher RNG cost in that as a sensitivity because we would have to go out and presumably procure more. So that's scenarios and sensitivities. So Brian, yep. So this table probably looks very familiar to everybody. I think we've shown it in most of our presentations. These are the 6 scenarios, 6 including the base case that we're doing. So I'm not going to go into all the details here because we're going to go over it on the different, we're going to do kind of a deep dive on each scenario. But basically, for each scenario, we want to look at what we may want to make changes to: customer growth, energy efficiency, renewable natural gas, hydrogen, gas bans, and then natural gas price, that traditional natural gas price specifically. Go ahead, Brian.
Are you still seeing that last slide?
yet. Does anybody else see the next slide, or is it just me?
There, it just moved.
Okay, I think we're good. Scenario 2. Yep, so that's where we're on. So the first scenario beyond the base case modeling that we did was a carbon neutral by 2050. So kind of as a point of clarification, when we say carbon neutral by this scenario's framework, we mean 0 CO2e emissions by 2050 as per CCA CPP guidelines. So basically, we're still going to be using things like offsets here offsets in Washington and CCIs in Oregon to be able to hit that 0 emissions. It's not going to be like a pure RNG portfolio, for instance. So in this, customer growth is going to be based similar to our base case. It's going to on a base 2023 load forecast. Energy efficiency. So this kind of gets to that point that Kim had made earlier. This is the first time that we are introducing that higher energy efficiency forecast using that higher commodity cost. And that higher commodity cost is that blend of RNG and hydrogen based on what's taken, that's used as the commodity input for the avoided cost. Now, the avoided cost calculation is somewhat tricky because it's not there are some things, especially here in Oregon, that, you know, through the UM 1893 process, we're kind of not dictated, but we have a process of agreed upon inputs for a lot of these variables. So we didn't want to go ahead and make that our base case before really talking about it through some UM 1893 stakeholders, maybe talking to some of the other utilities about it. But that is something that we feel strongly is a good it's a good potential change that could be something we want to look at in future IRPs as more of a base case, is not just looking at the traditional gas forecast, but really looking at some sort of blend utilizing the costs from RNG and hydrogen as well when trying to figure out that commodity cost. RNG availability. So this kind of gets to the point that JP was talking about, that JP and Kim actually were talking about, as to how do you exactly determine what is your RNG potential, right? So as I said in chat, I'm pretty sure we've had this conversation already. I think I talked about it during tag 3, and I may have even introduced it in tag 1, but I think I did a deep dive during the presentation in tag 3 about how do we figure out that RNG availability. But basically so in the base case, you may recall, it's going to be it's going to be a mix of the high/technical potential of that AGF ICF study, that American Gas Foundation study back in 2019. And so the cascade weighted share element is our attempt to account for those factors that JP and Kim kind of referred to. The things like we're going to be competing within our own state, our states, I should say. Northwest Natural, Avista, Puget, all these players are going to be making an effort for that. But it's not just them. There's also going to be transportation customers that are going to need to have their own reduction goals that are going to be going for it. And there's other states as well, not just in our territory. You know, there's a nationwide push going towards getting these RNG attributes. That's really it's starting to become more competitive. So for now, what we basically wanted to do is took our weighted share. So looking at how big of a fish we are, for lack of a better term, versus the national scale. So, you know, using EIA numbers for, you know, how big are we relative to others, we took that as our potential share of that AGF ICF study. It's not a perfect process, obviously. That study is from 2019, so there's still some updating that could be done on that potential. As RNG is becoming much more desired, more projects are coming online. You're seeing developers really take greater interest. So there may be more available in that regard, but there's also competition. So as we're continuing to play in this marketplace and acquire these projects, I think we're going to be able to have more refined assumptions. But this is what we're going with for this IRP. Kathy, you have a question.
Yeah. I was just wondering, okay, you're planning on buying the environmental attributes from renewable natural gas that's generated somewhere else and not guaranteed to come to Oregon. Do you have any idea of how much renewable natural gas will actually be delivered in Oregon versus how much is covered by the renewable thermal credit environmental attributes?
So that's a great question.
Yeah,
I
mean,
can tell
we
you that
realize that some of us are not happy with being able to spew out the
100%.
emissions in Oregon and not have to
100%.
account for them.
Right. And you know, our primary responsibility is complying with these legislations as they're written, and however they end up being written is how we will ultimately end up complying with them, right? So Brian kind of alluded to this a little bit earlier. For instance, Washington initially didn't allow this sort of system. Now there's some talk that there may be some sort of regional allowance. We're going to comply based on whatever the rule is. One thing I will say though is, for me personally, many of the projects that I have been evaluating, because I do a lot of the RNG cost-effective modeling for Cascade, and many of the projects that I've modeled have been localized projects. You know, we've gone public talking about the Deschutes landfill. That's a big one for us, obviously, and that is local, not just local to Oregon, local to our service territory. Bend is one of our city gates. So that's one we're very excited about, and that will have a localized impact for Oregon. There's definitely, I will say, speaking just qualitatively, I have seen that at this point, I've probably done more review of local projects versus just those attributes. Because those attributes are a trickier marketplace. Typically, I do think when you can do it, if you can be at least partially a developer of a project, if you can invest in that project, you typically are able to see a better return in terms of the price being more attractive versus just going to a third-party marketplace and having to pay $25 per decatherm just for an attribute, right? Like, that's a little bit high, but it does typically seem to be more cost-effective when we operate in that local space. But there's also limitations on quantity that's going to be available, right? So I think that's definitely where we're going to have a lot of our focus, is in that local space. But ultimately, we're going to do everything we need to do to comply.
Plus, if it's done locally, then that makes it more likely that you'll get it.
Exactly.
You can keep it.
Exactly. And that's
use it.
obviously a great consideration. You know, even the brown molecules, right? Like that's an important consideration as well. When it's a local project, that's ability to displace needing to purchase gas, there's a savings for that as well, versus just getting a piece of paper that says you have a green certificate. You still need to then buy a therm of gas somewhere. So it's a consideration. We're going to make sure we comply, but at least for me personally, a lot of what I've seen has been local projects.
Okay, great. Keep it up.
Yeah, so that goes into RNG. Hydrogen availability. So this we've already had a conversation about as well. I'm not going to keep everybody for lunch by belaboring certain points, but I will talk about it because I think it is an important consideration. In this scenario, in kind of the more aggressive scenarios we see where we really need to push the limits to what we can comply, we do model potentially increasing the amount of hydrogen we could blend to 30%. Now, on the flip side, you'll see we do have a scenario where we restrict it to 5%, and that's because there is this uncertainty about what is the safe amount of hydrogen that you'd be able to put onto your system and not risk damaging appliances, damaging pipelines. For this scenario, we model blending up to 30%, and that would only be done after a robust study, as Brian mentioned earlier, where we were able to conclude that it would be safe. Safety is a top priority for Cascade. We would not do anything like this until we were able to conclude that it was safe. But if it were, presumably in a carbon neutral situation, we would do a lot of investment in the research of that safety to see if it is technically feasible. But if it were, we want to model it at a 30% blend. Now, the question was actually asked to us from our friends at the WUTC, what is the impact of doing this? So what would it look like if we could only do 20%? And we did model that. I'm pretty sure we are still able to hit our emissions reduction compliance. It is just going to be a little bit more expensive. And that's to be expected, right? Especially in those later years, hydrogen is a very cost-effective resource. And that comes from just obviously a very broad assumption about the cost of hydrogen, but you know, from other sources, we do believe that hydrogen will decrease in cost over time as it becomes more invested in technology, more tried and true. There's more refinement to it. It becomes cheaper to to capture that hydrogen. We do believe it will be a more cost-effective technology over time. So you want to try to get as much of it as possible, but you're still going to want to keep it safe, right? So if we could only do it at 20%, it would be slightly more expensive because then we would have to go out and either buy more CCIs or buy more RNG or more attributes or invest in more local projects, or in Oregon get more allowances, or in Washington get more allowances. So that's really the only impact of it. It's a marginal impact to cost, and we can talk about that in the actual IRP document, what that would be, because we have gone ahead and done that analysis. Natural gas bans, so that's still all the expected bans that we're looking at. So most of that is going to be in Washington and Bellingham. There's the gas bans where we've made a quantitative impact to our forecast based on that. And then also consideration of some of the work that we're doing in Bend to try to make sure that we're complying and being a good partner with them about their considerations towards environmental goals. In terms of the traditional natural gas price forecast, that's the last element of this. We show a 10% downward adjustment to the price forecast. That's because we would figure if we're going carbon neutral, probably a lot of the players in this area are going carbon neutral. So there would be a less of a demand for that traditional natural gas. Prices at Sumis, Rockies, ACO may see a decrease because there's going to be less demand from rather large players such as ourselves towards buying that. We do also forecast for this a higher price of RNG above and beyond the base case. And that's kind of the flip side of that coin, right? As we're going out and buying more RNG, we've already picked the low-hanging fruit. We really have to kind of push towards the highest stuff. That's going to be more expensive. So we end up pricing that at $26 per decatherm to emulate the fact that that's going to be a more expensive resource. The next slide, we can go over some of the results of this analysis. Oh, Kim, you have a question.
Hey, Devin.
Yes.
Can you go back to the last slide just for a moment?
Yeah.
And I'm not sure that I caught everything about what you were saying about updating what it costs in 1893 as you're sort of learning more about how to iterate on this in the IRP process. But I am wondering about sort of the timing of the CPAs and whether whether you think the CPAs you have really are adequately reflecting the avoided costs sort of as much as you've learned to date, and whether there's a need or the ability to get back with, say, Energy Trust to update the CPAs if that hasn't already happened. Forgive me if I missed that.
So talking about the higher pricing that we're seeing.
Yeah.
So I think we actually, I don't want to say this without being certain, but I think we may have had a conversation like this in one of the tag meetings. I know we've had a conversation about this internally for sure. The answer we have for that is much of the pricing shift we've seen is short-term, not long-term, right? So if we look at the long-term fundamentals of the market, so going out, even just looking at forwards going 5, 6, 7 years in the future, those are still pretty consistent with what we were seeing when we first had the CPA run. So since this is a long-term plan, I don't think there's been enough of a long-term paradigm shift that would merit a recreation of the CPA. That gets back into that point in time nature of the IRP, right? We have to eventually lock things in, and things are kind of built off of other processes. So I don't think it's been a groundbreaking shift long-term speaking as to what we believe our DSM potential would be, based on the fact that I don't think there's been a significant long-term shift in gas markets.
But I guess what I'm missing is whether it was able to capture and reflect just the CPP, as a policy and the assumed changes associated with that lever. Right, because it's not just the market, it's not just for prices. Like you've got like a major policy shift that I would expect to see sort of reflected in, that CPA.
Sure. So thinking about the elements of it that could be, I'm sorry?
Oh, I didn't say anything.
Oh, so thinking about the elements of the avoided cost calculation, I do believe CPP compliance is accounted for in it, because it's one of those things that we were aware of the CPP as we were first running the conservation potential assessment. So elements like the carbon compliance cost of it. Now we use the social cost of carbon, but that tracks fairly close to the cost of CCIs. So I think that element of it is captured in the avoided cost. Obviously, we talk about commodity costs, and the higher commodity costs from RNG and this sensitivity, I think, helps capture that element of it. Distribution enhancement costs are talked about. We talked about that a little bit. I alluded to it in the conversations that we had when it came up with Kathleen, but that's an element. The offset of those programs is counted for in the distribution system cost element. And then there's also the risk certainty, right? There's the certainty of DSM versus the uncertainty of being exposed to markets, and that's accounted in the risk premium. So I think most of the elements that the CPP would have on the avoided cost are accounted for. But I'd be interested in feedback if you believe there's something else that maybe isn't accounted for.
Yeah, thanks. I think I need to get it in front of me and dig into it. But I mean, I feel like you've hit on a lot of the things, and I don't know, maybe yeah, I'd like to look at it some more. It looks like JP's got his hand up too, so maybe.
Absolutely. Yeah. Do you have our and if you don't have access to it, I can send it to you. But the filing that we made for UM 1893, because I know that was only a couple of months ago.
Yeah, I figured I would go check with Anna, honestly.
Yeah. Anna can probably get it to you, and that shows all of the elements. It's broken down really nicely, all of the elements of it. So if you feel there might be something missing, definitely do let us know. And if it's dramatic enough, we can see if it needs to be a change for this IRP or for a future IRP. But please do let us know.
Great, thank you, Devin.
Hey, Devin, this is just a follow-up to what Kim had. So for the 15 million therms, 12 to 15 million therms of RNG that are necessary, like by 2023, you're saying Energy Trust has that already built in to the forward price of your commodity, right?
In these sensitivities, they would. So in these sensitivities,
okay.
Yeah.
So and then just to take that a step further, the whatever, let's say the 2033, I don't know, 2030, it depends on the scenario that you guys have that you modeled, but let's just say the 30 to 40 million therms of RNG that you guys start needing. Broadly speaking, you're seeing that price in 2030 being equal to or less than the natural gas price. So that additional higher volume of gas is not any more expensive than the natural gas, and thus wouldn't be. If I'm interpreting what you're saying correctly, the renewable natural gas is going to be close to price parity with natural gas sometime in the 30s. Is that right? And so thus it's not driving up.
I don't know.
If
I said that, I apologize. I would not have. That would have been a misstatement. In the avoided costs that we send to Energy Trust, specifically related to these scenarios, the commodity cost element of it would have included a blend of the RNG and hydrogen, depending on what blend of those resources are selected. And it definitely is a higher cost. I think, in fact, come 2030, we project, once again, that whole low-hanging fruit going away, similar to what Northwest Natural did, where they priced RNG at tranches. We took the same approach. And so I think 2030 is when we actually start to see that the tranches kind of start for RNG going into that $19 per decatherm. So it's definitely more expensive. And in these scenarios, it's captured in that commodity cost element.
And I appreciate you just being so on point about this, but just and so I think anyone from Energy Trust is here, but like, so the current UM 1893 filing, that forward price would be reflected in there. Is that correct?
No. Okay. No. So thank you for clarification on that. So yeah, I guess let me take a step back. When we do our CPA versus UM 1893, it's two separate processes, right? Because our CPA is more of a Cascade specific CPA, while UM 1893 is the requested inputs, us providing those requested inputs. So the inputs we would have provided for UM 1893 were specifically the most recently acknowledged, the base case inputs, because there's two inputs we can provide, right? There's the base inputs and then the alternative inputs. The base inputs we would provide would have been our 2020 IRP acknowledged avoided costs. So the commodity costs associated with that. The alternative price we did was still just, for that process, was still just the commodity cost for traditional gas that we were seeing. And that came because we hadn't heard anybody else talking about it, and we didn't feel, without a kind of region-wide or statewide discussion on if a different input should be provided, we didn't want to go and provide something that may or may not have been in line with what other people were doing. So it was our understanding that it was still wanting to be just the traditional commodity elements. So that's what was provided for UM 1893. However, we have a little bit more flexibility for what we do in our IRP. And so for our IRP, for a separate CPA that we have, Avoid Energy Trust run for us, we provided, once again, two separate inputs. The first input being a traditional commodity, and that, Brian, if you go back a slide or two to the table that shows the different ones. Yeah, this one. So anywhere where it says CPA projections, that's going to be based off of the traditional commodity cost. But anywhere where it says scenario 2 CPA projections, those are based off of a commodity cost that's a blend of RNG and hydrogen. I know that's very confusing. I hope I clarified that.
Yeah, that's great. Thank you so much. I appreciate that.
Awesome. Sounds good.
Hey, just while I have you on here on scenario 2, the carbon neutral 2050.
Yeah.
I have been doing some reading up on like gas wells and their relationship to actual, I guess, oil wells, and like how drilling is, natural gas is generally not what you're drilling for most part.
Associated gas.
Yeah. Maybe this is offline conversation for the next IRP, but like as more and more states have mandates for electric cars, the actual demand for oil going down, and like those wells or new wells not being drilled, and potentially wells being shut down for oil, and thus kind of limiting the natural gas. Is that something you guys could explore?
I think that's a great point. I know. So our price forecast, I think we may have talked about this a little bit in one of our older meetings. Our price forecast it's kind of a proprietary blend of a number of factors. So we look at price forwards, we look at Wood Mackenzie, EIA pricing. So we look at a number of different factors when we are coming up with our price forecast. Presumably the people that create those forecasts, I would imagine that they're thinking about those stuff, because that's what they do all day, every day, right? So I'm presuming they're thinking about that and incorporating that. Forwards almost certainly are, because you've got people who are trading this on a day-to-day basis. I'm sure they're thinking about that. So I would imagine that is being reflected in those price forecasts that we are ultimately combining to create our one price forecast. But it's a great point too, and it's something that I think, not to go into too much of a tangent, but when we start thinking about our hedging plan, right, and we start looking at how those things are trending, that probably affects that process. So there's a number of different ways that could be incorporated. So my short answer is I would imagine that's being incorporated from the people who are generating those forecasts that we are then blending to create our forecast. But it is absolutely something I'll want to look into to make sure.
Yeah, I mean, if you guys, not a to-do item, but other than just if you could look into it by the time you guys publish the IRP, just to confirm that'd be great.
Sure.
Thanks.
Okay, so I think we've talked about everything on this slide. So the next one kind of showing some results now in this scenario. So unsurprisingly, once we get to those results, one thing you'll see is that the traditional cost goes down in this scenario, right? And that's to be expected mostly because of that last element on the natural gas price, the 10% downward adjustment. I'll wait to see Brian.
I'm not seeing scenario 3. I'm only seeing scenario 2.
Yeah, so this is what we want to see. Yep, scenario 2.
Okay,
Compared to the
different
base
slide.
case, yeah, you'll see that the green line, the green solid line is lower. And it's mostly driven by changes to traditional costs. And that actually ends up more so offsetting any additional costs that we would have for environmental compliance. So you'll see the total cost line is also actually lower than and that's the dotted line, is lower than the base case. So on paper, that sounds great, right? Going into a carbon neutral scenario could theoretically lower our costs. There are some things to step back with that, obviously. It is reliant on our assumption about pricing being correct related to traditional natural gas. So if that is correct, though, this is something that could be really interesting for us to explore. So this I thought was a cool takeaway for us. And if you go to the next slide, Brian, we'll kind of talk about some of the other takeaways that we had from it. But instead of it being, instead of it being automatically a higher cost, it could end up ultimately being a lower cost. But actually, first we wanted to show what our emission stack would look like. So to reach that carbon neutral by 2050, you can see we are able to hit it. So at no point do we have any deficiency. RNG is obviously going to be a massive part of this, and hydrogen is going to be a massive part of this. And that actually is the second reason why costs are lower, is that 30% blend assumption. Now, once again, that is an aggressive assumption. We do recognize that. But if we were to increase that blend to 30%, especially in those later years, that's a very affordable resource that would be a significant part of our portfolio, as you can see by the width of that green wedge. That would drive costs lower and kind of offset some of those costs for the need to lower our emissions further. So it's going to be something worth considering. At least, we'll have that qualitative analysis on it as to, the pros and cons, the impact of a carbon neutral by 2050 scenario. You can go to the next slide, Brian. So this kind of the key takeaways. I've already summarized most of them, but we do believe we'd be able to hit our emissions. We would need that aggressive utilization of green hydrogen, which comes with the pros and cons that I've already talked about. And then if those market conditions were able to manifest, being the declining pricing of hydrogen, the lower price of traditional natural gas, the cost would not be a barrier to accomplishing this goal. So it's an important consideration. It's something that I think, putting that qualitative analysis and us being aware of that as a company is going to be good to have for this IRP. So the next scenario 3, is limited RNG availability. So the main elements of this is, what if, the points that JP and Kim were talking about, what if there is too much competition for RNG? What if stagnating technology ultimately leads to us acquiring less RNG than we thought we'd be able to get? And on top of that, what if that stagnating technology ends up leading to lower hydrogen blends than we would initially think we'd be able to do? What does our compliance picture look like in that scenario? So growth doesn't change. Energy efficiency is using that higher energy efficiency forecast, because we would need to invest in more other resources if we're not getting as much RNG. So we would presume that we're going to want to go ahead and invest in more energy efficiency. The RNG availability shifts to that low potential of that AGF-ICF study. Hydrogen blend goes down to 5%. The gas bands stay the same, and the natural gas price stays the same. And so you'll see the impact of this one. So this one has a caveat, right? This is going to be one of those scenarios where I think we are showing an inability to hit compliance. So that's why you'll see the costs starting in 2040 get significantly lower. It's not because we found some magic solution, but there would be a challenge for hitting compliance in this. And I think if you go to the next slide, Brian, we'll see exactly what that looks like. Yeah. So you start seeing that gap in 2040, where if RNG does not manifest to what we would hope it'd be, and then CCIs, obviously there's only so much we can purchase in CCIs. Green hydrogen is now a extremely small wedge. We're going to have challenges to hit our emissions goal, even with a more aggressive DSM approach. And so on the next slide, we kind of talk about what does that mean? Does that invalidate this portfolio? We'll talk about that in the key takeaways. So we do believe we'd be able to hit our goals in Washington, and that's because Washington does have this auction marketplace where we do believe we would be able to participate and offset any need for emissions reduction goals by purchasing allowances in this auction. But we would have a challenge to meet our success in hitting the goals in Oregon. The biggest takeaway for this is we're going to need to keep being aggressive in our pursuit of RNG. Now, while we would be in compliance, so for that period we were in compliance, our costs were typically higher in a limited RNG scenario, but not prohibitively so, because we're going to have to, we lose out on getting as much RNG as we want, so we're going to have to look at higher cost options. So those CCIs, eventually, as they continue to increase in cost, they're not as cost effective as RNG, so we have to invest in that. And then particularly in Washington, the auction allowances end up becoming more expensive. We have to invest more in those versus other options. So the reason why we don't invalidate this as a portfolio is because of the time frame of the gap. So normally the IRP is a 20-year plan. We extend out to 2050 because that's where the emissions reduction goals end up happening. So presumably we would want to end this IRP around 2042. For the most part, through most of the planning horizon, we are still able to hit our emissions reduction goals. So in the short and midterm, and even long term from an IRP perspective, we're not too concerned. Now, from a long-term perspective for just the global long-term plan, obviously hitting 2050, it is a concern. And that, once again, it gets to what is that key takeaway from this plan? And that key takeaway is going to be that RNG pursuit. And that's why we have a lot of company resources dedicated towards the evaluation of these projects, towards looking at those RNG attributes, towards conversations with Washington about will we be able to use RNG attributes beyond just what's able to be produced locally in the state. Aggressive pursuit of RNG is going to be, in my opinion, the most vital element to our success with complying with these goals. Scenario 4, so increased electrification. So this one came right out of the UM 2178 proceedings that we had, where we wanted to look at electrification. We think it's important, specifically from a rate and bill impact element. We want to look at what's going to happen in those elements if we were to be in an increased electrification. So the assumptions from that came right from UM 2178. Customer growth gradually slows to 0 in 2025 and afterwards, and then residential and commercial customer counts, are reduced to 10% of what they otherwise would have been by 2050. So that's a significant loss of customers from electrification. Energy efficiency, we're going with the higher forecast because presumably part of the electrification effort would be also increased energy efficiency from our customers. RNG availability and hydrogen, we're going to keep the same. For natural gas bans, now we're looking at all expected and proposed bans. So anything that any of the counties that we're looking at, I think Whatcom County, for instance, had a ban that's part of this. Anything that's considered, because electrification is the element of this scenario, is going to be something that's going to be a part of this. So those natural gas bans are a part of this scenario. And that's what ultimately ends up making those customer counts reduced to 10%. We also forecast a downward adjustment to the IRP price forecast of 10%, that traditional natural gas forecast. And that's similar to what happened in scenario 2. There will definitely be less regional demand from the gas companies if an increased electrification world happens, because we're all going to lose customers. So with lower demand, prices would fall in that scenario. So we assume that 10% adjustment. So looking at the cost in this one, obviously on paper, to some, this may look fantastic, right? So the blue is what our traditional cost is, and that actually ends up being lower as well. That's mostly driven by that adjustment to the price forecast, but also by virtue of the fact that we have less customers. So we have less costs. And then obviously the total cost, which includes environmental compliance costs, those are significantly lower. And that's because, once again, by having less customers that we'd have to serve, by having lower emissions, we can really only focus on the cheapest resources, the lowest of low-hanging fruit to hit those emissions reduction goals. However, I caution everybody that this is two things to consider with this. For one, this is just a Cascade-centric perspective of this. This does not look at the flip side of the coin for electrification, and that's who's picking up those costs. Well, it's going to have to be those electric companies that are now being the ones to serve those customers. Are they going to be able to do it at a more cost-effective rate? I think the only way to do that is going to have to be through a regional analysis. And that's something that I know a lot of people have talked about. OPUC has definitely expressed interest in trying to see that happen. But I think that's something that before we can draw any significant conclusions about, is this a good path to go? What do these costs look like? That full holistic analysis needs to be done to see what ultimately is the result of cost on a apples to apples basis. For every customer we lose, another electric utility picks that customer up. What is the result of that customer to customer analysis, and does it end up being cost effective holistically? Because this may look great for us from a cost basis, but it may not necessarily look great for them, and it may be a more expensive resource for them that ultimately ends up costing ratepayers more money. And then the other impact is what's going to be those bill impacts. With a lower customer base, these costs are chopped up by less customers, so it's spread out over less customers. Those bill impacts are going to be significantly higher. We don't have the exact numbers finalized yet, but having seen at least the preliminary numbers, they're significantly higher just because these costs are socialized or spread out over less customers. So that's a potential red flag from doing this as well. And we'll talk about that in the actual narrative. We'll show those rate impacts, but those are the two things that I advise you when you see this to really keep in the back of your mind about why the cost may look great on the surface, but there are significant problems that we would be facing, challenges that we'd be faced from this scenario. Brian, if you go to the next slide. This just shows what our resource stack would be. Obviously, once again, it's going to be quite easy for us to hit emissions compliance goals with this. Hydrogen would still be a rather large part of it, RNG to some extent, and then CCIs to some extent. Some mix of those resources would ultimately be how we would presume to hit those goals. And the next one, kind of those key takeaways. I've already talked a little bit about them, but I do want to highlight some of it. So the increased electrification would make compliance easier, and the costs are lower to Cascade, but it's a result of those costs being shifted elsewhere. So before any policy decisions would be made on this, that apples to apples comparison really is what's important to look at. And then lower costs, once again, do not necessarily reflect lower rates, as customer counts lead to higher costs per customers. We are performing this rate impact, and it'll be included in the final IRP. Like I said, we already have draft numbers, and I can tell you it's a significant increase to customer bills in this kind of lower customer count scenario. So the flip side of that is, what if it's a high customer growth? Now, this was a much more popular scenario in past IRPs, but I think it is still an important scenario for us to run. Our growth projections may be lower than expected, and there may be other vehicles, that lead to us to grow customers, but we still want to be sure that we can comply with the CPP and CCA with these with higher customers, if that is ultimately how our growth ends up manifesting. So the customer growth is our high growth projection. So Ashton looks at the higher interval of those growth projections for this. We would presumably want higher energy efficiency, because if our growth's getting higher, we're going to need to invest in more energy efficiency as one of those resources to help hit those compliance goals. Same with more RNG. We're really going to have to aggressively pursue RNG and get those higher hanging fruit, for lack of a better term, the ones that, as you'll see at the bottom, those $26 per decatherm items. We really would need to go ahead and pursue those to make sure that we can hit those. We also look at the higher hydrogen availability, and the gas bans are still just what's expected. So looking at the cost of it, unsurprisingly, the costs in this one are more expensive. We're going to have to pay, just by virtue of having more customers. This isn't looking at revenue or anything like that. This is just cost. We have to end up ultimately serving more customers in this. So both our traditional costs and our total costs, which includes environmental compliance costs, are higher. And the one thing you can see is the larger difference is from that environmental cost. Most of the increase is not from traditional costs. It comes to the fact that we would have to buy quite a bit of that $26 per decatherm RNG, just to make sure that we can hit our compliance costs. or hit our compliance goals. Sorry about that. And the takeaway is we can. So this is what we do see from the stack is obviously we're procuring more RNG. We're maxing out that green hydrogen, but we are able to hit our compliance goals under the constraints talked about before, which is a really good takeaway. That really helps us feel confident from this scenario that we are able to hit those compliance goals, even if growth is higher than we expect. So we are pleased to see that. In Washington, one key thing that we're going to have to do is heavily participate in those auctions, right? So as we are, I don't want to talk too much about this because this is an Oregon-centric tag meeting, but basically they have the auction mechanism where you can offset your emissions by purchasing one allowance. And there's the entire very complicated auction mechanism through which you can do that. We would want to be aggressive in our participation with that because that is a very cost-effective resource. So a combination of being aggressive in that, aggressive in RNG acquisition, and hydrogen, higher hydrogen levels, if possible, are going to be key to our success in doing that. The costs are higher, though, and that's mostly driven by those increased costs related to emissions reduction requirements. Now, under one thing that's always important, and Brian talked a little bit about this, when we do that value at risk analysis, we always want to make sure that cost increases are not cost prohibitive. Now, that's obviously a qualitative assessment, but we do look at it and say, okay, is that difference that you saw, the difference between those two dotted lines, is that significant enough for us to reject this portfolio? We don't believe it is under deterministic modeling. However, as Brian mentioned, we're kind of in the depths of doing some stochastic modeling on scenarios like this. And that's one key takeaway that we may find out from that, right? Is under a 99th percentile of pricing environment, do we end up ultimately seeing costs that are just too high to tolerate? And in that case, do we need to look at a different solution, a different portfolio? To be seen, and we'll report on that in the draft IRP. So the final scenario, this was actually kind of a fun one to do. We wanted to, and I talked a little bit about this in some of the prior meetings, but we wanted to model what is the impact to our portfolio if these indiscriminate, stochastically driven incidences cause disruptions in the availability of our traditional natural gas at specific basins. So we've talked about this before. In the past, we did these scenarios where we would like just straight up cut off all the supply at Sumis or all the supply at ACO, and then have the model try to run through that. Now that's not really plausible. That probably it could, but that probably won't happen over the 28-year planning horizon. But what can happen is incidences do happen. So obviously, I don't want to pick on Sumis, but the Enbridge explosion happened in 2018, and that was a major incident that caused a loss of availability of Sumis gas, and that the entire region had to account for. And when that happens, you see two things that happen. One, the obviously amount of gas you can buy drops way down, and the price shoots way up because let's say you can only get 10% or 20% of the gas out of a specific area and everybody wants it, that's going to drive the price up. Conversely, you're also going to see prices go up at the other basins, usually not as much, but there will be a correlated increase because people are going to those basins to buy it as well. So we wanted to run this scenario where we stochastically derived, where we would pick random times and it would be done just based on a probabilistic model that we developed. That'd be okay. As time goes on, if an incident hasn't happened, you increase the likelihood, and then bam, all of a sudden you have an incident happen randomly at one of the basins. You randomly determine how much gas is cut, and then you shoot prices up to the 99th percentile of our stochastic pricing. That seems to be a reasonable way to say, okay, that's a reasonable amount to see how high that prices could end up going. The 99th percentile is typically a good statistical barometer of that. And then, once again, a random amount based on how much supply is cut. So we end up running that through the 28-year planning horizon. And I think we ultimately have 3 incidences that are modeled in this scenario, one at each basin that just randomly happens at a time across the planning horizon. And this lets us see what the impact is to both cost and resource takes. There's actually a really interesting result that happens with hydrogen that we'll go into a little bit later once we look at the resource stacks that ends up being a result of this. But we'll talk about that more when we see the actual figures. But basically, that's how this works. We model these indiscriminate incidences and see what happens to the portfolio. No change to growth, no change to energy efficiency, because all of that stuff would still be what we normally deterministically expect to happen. So we're going to keep that as our deterministic assumptions for those. Same for hydrogen assumptions, same for RNG assumptions, same for gas bands. And then price, we talked about what ends up happening with prices when those spikes do happen. So looking at the costs. All right, so first I wanted to show, this is kind of a cool little figure to show how those incidences actually manifest in terms of both price and in terms of supply. So price on the left, you can see that there's 3 incidences that happen. There's the one on the first incident, I believe, was at Rockies, the second incident at Sumis, and the third at ACO. So one question that you might have from this is, why is the Sumis spike higher in the ACO incident? And that's just because Sumis is a much more volatile basin, right? Sumis pricing, as we're seeing right now, it can go even under normal conditions as high as $10, as low as $2, let's say. So when incidences do happen, there's a lot more volatility that can spike Sumis. But ACO going up to, in this, a little bit over $15 would still be a significant incident for ACO. So that's kind of how the pricing ended up happening, is you still are constrained to what the natural volatility is of these basins. But it creates those pricing incidences that I think are cool to evaluate and see what it ends up ultimately having on the portfolio. And then the supply, you can kind of see how it manifests. So this is just using that fixed resource. There's other supplies. This is not all the gas we have at ACOs, Rockies, and Sumis. But this is just for illustrative purposes, what happens to one of those supply resources from each basin. So when the Rockies incident happens, you see the Rockies fixed go down to 0. When the Sumis incident happens, you see that one go down to 0. And then when the ACO incident happens, you see that one go down to 0, or almost 0, and then slowly start to crawl back up. Most of them actually have that increasing pattern that you see from ACO, because eventually we do slowly increase the amount of gas that happens. This is just the optimizer choosing, let's say, less of that fixed resource and more of, let's say, that day resource. Which I don't want to spend too much time on, but the long and short, the short takeaway of it is, when the incidents happen, supply is significantly cut out of basin and then price goes way up. I think you might be on mute, Abe. Or your headphones might be on mute, because I don't see you on mute, Liz.
Yeah, can you hear me now?
Yes.
Yeah. I don't know if you use LNG or not, but do things like world events, climate change events affect your LNG supply prices?
So we don't, I mean, we have storage facilities, which use liquefied natural gas.